we're just connecting. Oh, you can just do it. Oh, okay.
Oh, really? So I don't have to be on Zoom at all? Oh, awesome.
Yeah, let's do
Sure.
that.
Hello.
Okay.
Can you hear me?
Hit Chrome. Yeah. Hi. Yeah, we can hear you.
Oh, great.
It's a little muffled though. I have to.
You can't hear me well?
We can hear you, but
Slightly muffled.
yeah, the sound quality is a little crummy.
Okay, let's try another one. About this one?
This is a little better, actually.
Yeah, can you hear me well?
Yeah, I mean, yeah. One sec. We're gonna check.
Okay.
Okay. Okay.
Test.
Hello, can you hear me now?
Yeah, Daniel, we can hear you. People are still coming in. You're the first talk of the morning, so we'll probably start in a few minutes.
Okay, and how long is the talk, just to make sure?
50 minutes? 50 minutes plus 10 minutes for Q&A.
Okay, great.
Good morning, DeepMath, and welcome to our second day, hopefully a calmer day. I'm delighted to introduce Professor Daniel Sudri from the Technion. Daniel and I actually did our bachelor's together in physics and electrical engineering at the Technion way back when. Daniel then went on to do a PhD in electrical engineering at the Technion and a postdoc at the Department of Statistics and the Center for Theoretical Neuroscience at Columbia. He's since then has been a faculty member at the Technion, and he is also a Schmidt Career Advancement Chair in AI. Today he'll be talking to us about catastrophic forgetting and linear regression and implicit bias of minima stability.
Thank you, Gal. Many thanks for inviting me here to give this talk. I'm really excited to be here, at least virtually. So this is a two-part talk. Hopefully I'll be able to squeeze both parts in. I think there might be both interesting, and at least one of them should be interesting for one of you, for some of you. Okay. So the first part is about how catastrophic can catastrophic forgetting be in linear regression. This is joint work with my student Itai Evron, postdoc Eduard Moroshko, and collaborator Rachel Ward and Nati Cerebro, which was published in Call 22. So first, what is continual learning? For those of you who maybe not completely familiar with this term. So in continual learning, we have tasks which arrive sequentially, each having its own distribution. For example, we have an autonomous vehicle and we're learning a task for it to drive in the morning. And then we want to have a task which is slightly different, driving in the evening and then driving at night. Each task has a different distribution of its inputs. So the goal is to try to learn this model sequentially on each task, and then the other task. And then in the end, we want to succeed all tasks together. So the problem is that upon learning a new task, the performance deteriorates on previous tasks. So this nice picture from Colori et al., where if we're trying to fit, for example, here a classification task between two classes, the blue and the red, using this nonlinear separator, and then we're learning another task on a different input distribution. then ideally we like the separator to be able to separate the data on both blobs of data. But unfortunately, because we did the second task without keeping the first task in memory, we might have an issue that the updated decision boundary will misclassify the previous task. So we have this degradation. We want to see how to remove this. So the common research and most publication on this focus on algorithmic and practical approaches for overcoming forgetting. However, what we want to focus here is why do we really have forgetting precisely? And we trying to answer this even in the simplest setting possible, where it seems that this answer is still unclear. So what is the simplest setting possible? Well, what we can think of, the basic example every machine learning course starts with, SGD or gradient descent even on linear regression. And we want to understand even there the basic questions. Can forgetting become catastrophic? Meaning if we fit sequentially to the task one after the other, won't eventually be able to fit all the tasks? Is it possible that we'll have this catastrophic forgetting, that we don't fit all the tasks? So just to spoil this lecture, yes, the answer yes, we can find an example, even a linear regression, that this can happen. Is it possible to prevent this without changing the algorithm, just some restriction on the setting? Yes, we show that if we repeat the tasks cyclically or randomly, or even just without repeating them using a randomized order, we can prevent this from happening. How does task similarity, meaning if the tasks are similar to each other or not, how does this affect the forgetting? So this is a bit conflicting in the previous literature. Duan et al. Suggested in a similar linear regression model that if you have high task similarity, the tasks are very similar, this will cause you to have the maximal amount of forgetting. In contrast, Li et al., which was in a different tool layer and neural network with parallel task last layer in 2 tasks, showed that intermediate task similarity leads to maximal forgetting. So even though this is a different model, it seems like the conclusion is quite different, which was kind of surprising. So the answer is, can we reconcile these different results? And we show that we can. So we show we can, and the actual answer depends on the number of tasks, and we can get from high to intermediate similarity, depending on the number of tasks we use. So to be formal, let's start with some preliminaries. A continual linear regression, we have a sequence of regression tasks, x1 and y1, x2 and y2 until xt and yt. Large T is the number of tasks. And we want to learn a linear model. W, it's a vector of RD, which we do it sequentially and then succeed on all tasks. We assume that tasks are jointly realizable, meaning there exists some W star, which perfectly fits to all the tasks. For xk times W star, we get the correct labels yk. So the simplest fitting procedure, again, we use is vanilla SGD or gradient descent. We initialize from 0 just for simplicity. And for each iteration, we start from our previous solution we got from the previous task, and then we minimize the quadratic linear regression loss, meaning xkw minus yk, and minimize this with either SGD or gradient descent until convergence. And then we set the solution at the end of the task as WK. And after we keep doing those iterations, after the number of tasks end, we just output our final weight vector. Okay, so what do we want to know? We want to know first how close we are to the solution. What is the solution? So there can be, in at least an overparameterized setting, could be many solutions, meaning all W such that the loss is minimized. It can be 0 if you're sufficiently overparameterized, and if we assume it's realizable, it will be 0. So there could be a different type of solutions which minimizes. We want to have the distance to this one of these offline solutions. And forgetting, which is the drift of the previous output. So we have an output in the final task. We want this output on all the tasks, meaning this is a W we get in the end. So the output on all the tasks using the W we get in the end will give us xkwk, which was what we had in the end of the k task. Okay, so this was also a definition of forgetting, just trying to quantify how our predictions have drifted from the previous predictions. Okay, just to note, the definition of forgetting is slightly similar to regret, but it's not regret. Regret is trying to quantify your error on future predictions, not the previous ones. So the solution of this algorithm is simple, right? This is linear regression. We know how to solve this analytically. There is a formula. You can get this in Wikipedia, or it's very, very standard, using pseudo inverse of wk x pseudo inverse yk plus this null space term. And you can rewrite this in a more convenient way, where in each time we do a task, what happens is that the distance from the offline solution, this is our distance, or like the vector of difference from our current W to the offline solution, is multiplied by this projection matrix. We call this PK, is just the null space of each task. And each time we do a task, what happened? We start with a task W k minus 1. We are in some solution space, and then we project using this null space operator to the next task. Okay, this is just algebra of rewriting the solution of linear regression. So once we do this, it's easy to see that when we do multiple tasks, one after each other, we simply multiply our initial difference vector from initialization to the solution by those different projection matrices. So when we do now another task, we again project, and so on and so forth. So what happened, because this is a projection matrix is contracting, it has eigenvalues which are not larger than 1 in magnitude, we always decrease the distance to the offline solution each time we do a task. So it seems that with more tasks, we should converge to the offline solution, right? So it should not forget after we do a sufficient number of tasks. We'll see about that. And forgetting, so what is forgetting? We define this quantity of how well we're doing on the previous tasks. So we can show this bound that forgetting is upper bounded by the average of squared residual, this quantity here. Just take the difference from the last task to the offline solution, and then do the orthogonal projection, the I minus the projection we had before, and we sum over all the tasks. So you can think of it as the complementary projection from P, that we're looking on the residual of our final solution from the previous task. We project back and then see what is the distance of this line from the previous task. And this, we sum the square of all those lines, we get the forgetting. So this is kind of the geometric view of forgetting in this case. So what can we say about this setting? So the first result is that forgetting, even though we are contracting and always decreasing the distance to the teacher, you can construct an example where forgetting can be catastrophic, meaning arbitrarily bad. Specifically, we can construct a series of tasks we showed here in this picture, where both quantities are arbitrarily bad. The distance to the teacher and the forgetting are both, can be arbitrarily close to 1 as the number of tasks go to infinity. The type of intuition we get for constructing this example is we have to keep a lot of tasks close together in the beginning. So we're doing a projection each time only on the circle. So each time we're not actually contracting a lot toward the center. And in the end, we do larger jumps. And when we construct it in the correct way, we can get the arbitrarily close to 1 in our forgetting in the end WT. Okay, so this can be arbitrarily bad. Even a linear regression can be catastrophic, forgetting. Can this be preventing if we restrict our setting? So let's look at the first suggestion. How can this be prevented? Repetitions. So what do I mean by that? So if you're in a cyclic setting, for example, tasks often in realistic setting can occur naturally in cycles, such as day, evening, night, as we mentioned earlier in autonomous vehicles. And if we have this repetition, then each time we have a projection to that task, and then we get the same projection again after a while. Okay, so after n cycles, we have what we get here is kind of a cyclic operator. We have the product of projection for one cycle, and then we do this to the power of n, which is the number of cycles. So this, if we can write it this way, this is actually a special case of the literature of alternating projection, which is well studied in functional analysis for the last, I guess, 60 years, or even more. Von Neumann, we see a paper there. So this is well studied. So let's see what we can say about that from that literature. So let's look at the simplest example of two tasks and what we can say there. So we have two tasks. We have one task, and when we project to the second task, and then we project back to the first task again, and so on and so forth, until eventually it seems like we should converge to the teacher in the end. So, so the theory of alternating projection, it's easy to see that this distance to the teacher, which is just the norm of the teacher times the projection matrices, this power of n, you can upper bound it by the spectral norm of this P2, P1 to the power of n, which under some scaling assumption that the norm of your teacher is not too large, bounded by some constant 1. And this was already solved exactly, and you can find an exact expression in it using the smallest principal angle between the tasks. This is this tau f. In 2D is exactly this angle we have here. In higher dimension, it's the smallest principal angle. So you have this cosinus, the square of the principal angle to the power of 2n minus 1. So the problem is that this convergence rate can be arbitrarily slow. If tau, this angle is going to 0, then its convergence rate can be very, very slow. In contrast, if we look on the forgetting, which was not in the projection, alternating projection literature, we get a different expression. We can bound the forgetting using this maximum I over principal angles. And we get this different 1 minus cosinus square here, multiplying this cosinus square to the power of n minus 1. And this product here is making a very important difference because these all two principal angles appear in both sides. When we optimize this and finding the worst case theta, we get an upper bound which is universal, meaning for all theta we can show the forgetting is actually decreasing as here 1 over n with some constant. So it means that forgetting will not be arbitrarily slow in contrast to the distance from the teacher. So just to visualize this, is this upper bound we have here. This is the blue line. This is the number of steps, and this spectral forgetting, this bound we have here for forgetting. And for different theta, different principal angles, we see that we get exponential decrease in the forgetting. But as we go farther and farther away, we can get, you can use different theta to get worse convergence. But this upper bound, which is polynomial, or sorry, power law, will get us the sharp upper bound on all those different exponential convergences. Okay, so it's nice we have this universal bound. And just another thing to say that without repetition, if you just look at two tasks, then we can use this bound and see that, analyze it and say exactly how does the theta affects the forgetting, or how this is theta, this is kind of the similarity between the tasks. And we see that the forgetting is 0 if we have theta equals 0 or 90 degrees. And for two tasks, we get the maximal forgetting, the worst case, when we have intermediate similarity between the tasks, an angle of 45. However, if we increase the number of cycles, we get smaller and smaller angle for the worst case forgetting. Okay, so this is kind of maybe explaining the previous result in the literature, where some works said that intermediate similarity is the worst case, while others said that you actually need the high similarity, meaning small angles. Okay, so we have also another more precise results for even generality, not just two tasks. We can show that forgetting after n cycles for a general number of tasks is upper bounded by this bound, which is the minimum between something which is the n to the power of 0.5 with t, and another one which is better dependence on L, but it has the dimension here. Okay, so this is one bound, and another bound we can show with random ordering, not cyclical ordering, either with or without replacement, that the expected forgetting after k task is 9 to the d over k. Okay, so the forgetting again here is the expected forgetting is decreasing to 0. There's no catastrophic forgetting possible. And because this does not depend on t, and we can do this even without replacement, then this actually holds without repetitions. It means that if we do random ordering of our tasks, even if we don't repeat them, we prevent catastrophic forgetting, which is nice. So what about empirical results in neural networks? This is actually similar to what we say here. So there was a recent paper scaling the number of tasks in continual learning that showed a similar phenomenon. What they did is they took each task, you sample 2 random classes and you sample data points from those classes. For example, here the blue and the blue and the red, the yellow and the green, and so on. Each task is a different combination of 2 tasks, two classes, sorry. And in the end, after some time, you just check the performance on all classes together. This is the test. And they used vanilla SGD in our other algorithms as well, but even in vanilla SGD, what they show that you can learn quite well all the tasks together, meaning the test accuracy is not so bad on a variety of benchmarks, which are popular in the continual learning literature. Okay, so just to summarize this part, what we show that even a linear regression forgetting can be arbitrarily bad or catastrophic, and there can show the precise exact effect of task similarity on the forgetting between tasks. And we can show that with cyclic or random ordering, forgetting diminishes linearly with the number of seen tasks. Other things we mentioned in the paper, but I didn't have time to talk about here, is we find conditions for 0 forgetting, more general than what we mentioned. Even we can find lower bounds on the rates, and discuss relation to other quantities such as regret, catch-match method, alternating projection, stochastic proximal point algorithms, NLMS, and many more. Okay, so thank you. If you want to read, there's an archive. Also, it's on Colt. Feel free to ask many questions in the end. And now to the second part of our talk. This part is about the implicit bias of minima stability. It's actually a combination of a couple of papers. The first one was with Roto Mulayov, Tom Michaeli, the implicit bias of minima stability of view from function space in NeurIPS. And the second paper, we had also Mor Spiegelnaxen, my student, and Greg Unge joined us, and this is currently under review. So our motivation for this work is trying to understand the behavior of neural networks in overparameterized regime. So if we have data points, here it's just univariate data from X to Y, and we want to fit it using a neural network, then we can get one solution or a different solution or third solution, a different interpolating solution. And the question is, to which solution does the optimization algorithm converge to? And so there are quite a lot of works about this. It's usually one of the ways to call this the implicit bias of this learning or gradient-based method. One of the first conjecture was this implicit bias is a kind of regularization that also might be useful for generalization. And this was proven, this behavior that gradient descent has this implicit bias in several cases. The simplest one is just very trivial linear regression. Under some assumption in matrix factorization, also with linear classification, logistic regression on separable data, and many other works afterwards. And the limitation of this is that this usually relies on some manifold property, as shown in Azulay et al., which does not always hold. So we can show examples where the conjecture breaks, that we can't really get some form of regularization from a gradient descent, for example, for a single ReLU or for a matrix factorization problem. So another issue that all of those works I cite here and even other below usually assume a gradient flow, meaning vanishing step size. And if they don't, they assume the gradient is small enough, so we're close to gradient flow. So we can't really say much about how step size is affecting the implicit bias. However, there is a large effect of the step size, as we show in this example. We use a single one hidden layer and null network with Rayleigh network, and we look at the loss when we train the network. It goes to 0. In the end, we perfectly fit our data points, and we get some function, which is this black line. And now we try a different experiment where we stop training at some point, increase the learning rate, and then continue training with this increased learning rate. What we see that we again perfectly fit the data points. However, we converge to a very different solution in which we actually are much less sharp in the function space, in the predictor, than the small learning rate behavior. So this interesting behavior could be useful also to understanding what happens in neural networks and their generalization, because it seems that high learning rates, of course, are needed in many cases to get good generalization behavior in practical neural networks. So in this work, we're trying to understand how a property of SGD stability, which always holds, no need to assume it, can explain this type of implicit bias, and how can you connect it to the step size, how the step size is affecting the solutions we get. So to understand what is this stability of SGD, so suppose we have two types of minima in parameter space. One is flat minima. So when we do gradient descent, we converge to this minimum quite well. However, if we use the same learning rate, if it's too high for the sharp minima, meaning even the same learning rate can be too high for the sharp minima, we will not converge and escape exponentially fast from that minimum. So we call this flat minima stable because we can converge to it. And here the other one is unstable. So for gradient descent, the condition for being stable is sufficient and necessary. It means the condition is that the maximal eigenvalue of the Hessian is smaller than 2 over the step size. For sharp minima, which are unstable, this is larger than 2 over the step size. So this is a necessary condition for SGD, but again for GD, it's also sufficient. So what can we say using this relation? So we can derive here, what I'll talk about is deriving a framework for analyzing, this I will not talk about, it's in the paper, analyzing stability of non-differentiable minima switching systems, and show that large step size lead to smooth functions, meaning specifically smoother near the center of the training distribution. And we verify this behavior experimentally. So in this talk, I will talk about the part which is differentiable, right? Because ReLU functions are actually non-differentiable. Some subtle issues about discussing stability with non-differentiable functions. However, this is more complicated, so I'll leave it for you to see in the paper. I will talk about the second and third part. First, we focus on the simplest setting of a not only shallow one hidden layer ReLU network, but even univariate, meaning the input is scalar. Okay, so we multiply it by weight W and add the bias B, and then a ReLU, and then multiply by another weight to add the bias B. So this is our predictor function. You can write it this way, and we sum over all neurons. So this is the ReLU function, and we look at the family of functions that can be expressed using this way, using k neurons. So this is just a family of piecewise linear functions which has k knots, meaning this non-differentiable changes in the slope. So we minimize some loss function. We focus here on the simple mean square error loss. This can be generalized, but we focus in this case for simplicity. And in the overparameterized case, the number of neurons is larger than the number of data points. Then this loss function can be minimized. We can fit perfectly all the data points using our neural network and get 0 error. However, there are infinitely many solutions, right? We are overparameterized, so we can set the neurons and parameters in different values and get this 0 loss. And we want to understand what is this what does it entail that we arrive to this minimum. However, when we are at some minimum there, we get some predictor function. And this predictor function can have two different implementations, meaning we can use different parameters to create the same function. With one implementation, we can get a sharp minimum in parameter space, and another implementation, we can get a very flat minimum in parameter space. So if we want to understand how this stability affects the predictor, we need to find what the implementation exactly we're talking about. So to do so, we define the space of all parameter vector that implement the same function f as this omega of f. And we look at the flattest implementation, meaning looking over the maximal eigenvalue of the Hessian, we take the minimum over all possible implementation for a given function. Okay, and now we would like to bound this flattest implementation, this stability, and we will show why this is useful. So our main result in this paper is that we can lower bound this flattest, the sharpness of the flattest minimum, meaning the maximal eigenvalue of the Hessian in the minimal case. And we can lower bound it using 1 plus 2 times this integral of the absolute value of the second derivative of the predictor times some weighting function g. Okay, so some property of this g, I will not write it, it's a bit complicated expression, but it's in the paper. It's a non-negative function which depends only on the data set. The data set meaning just on the data point, there's nothing else that goes into it. And most of its mass is usually located in the center of the data set, and it vanishes outside of this data distribution. And we have this closed form for g. It's an exact expression, just pretty long. And why is this useful, this result? So this is the function g for some specific data set of uniform data. This is useful because we know that for stable minima, we have that 2 over the step size is larger than the sharpness, meaning the maximal eigenvalue of the Hessian. This is true also for the flattest implementation. And this entails that this expression, which kind of is kind of a norm on the predictor, is smaller than 2 over the step size. So as the step size will increase, this expression must become smaller and smaller. And this here is a second derivative, integral of a second derivative. You can think of it as a weighted L1 norm of the second derivative. And the second derivative here is in the weak sense, meaning it's a non-differentiable function, so it will be a delta function if we differentiate this value. So what do we get from this? So if f is a stable solution for SGD with some step size eta, then we can say that this expression is smaller than 1 over eta minus half. And this is, when we change the step size, this will make things smoother or less smooth. So we assume for this theorem that our solution is twice differentiable, meaning the kinks of the value function are not falling exactly on the data points. Otherwise, they might be non-differentiable, and then we need to do some correction, which is in the paper, what happens when the data points and the kinks fall on each other. Okay, so we get a slightly different expression. And just to show to visualize our results, so here we show the data points and we fit some function first with a small learning rate. It's 0.0001. And again, we fit perfectly the data points, but the function is quite sharply changing. And here we plot in black the absolute value of the second derivative, meaning kind of how smooth the function is. And we see it should be quite strong. And in red, we show this g function for the data set, which we can calculate. And what we see that even at small learning rates, this g function seems to have some influence and causing the sharpness to decrease around the center of distribution. It's sharper around farther away from this center. As we increase the learning rate, the function becomes less fluctuating, smoother in some sense. And you can see this in the second derivative of the function. And again, it's smaller near the center of the distribution. And if we increase the learning rate even higher, we get even a smoother function. And we see that even for high learning rates outside of the distribution, we get still some fluctuation, meaning that farther away from the farthest data points, we do get some sharpness. So this matches our results. Okay, and now let's compare all the different bounds we had. So first we have 2 over the learning rate. So this is the learning rate in the x-axis. And if we examine the sharpness or the lambda max of the Hessian at convergence, we get often that this is equal to 2 over eta. Even though we should be it should be bounded by this, it's actually we see empirically that it's equal, and that's a phenomenon was called the edge of stability. The paper, for example, at Cohen et al. And this kind of tightness says that this part of the bound at least is very tight. Now we want to see what happens with the flattest implementation, not the exact implementation we converge to, but the flattest implementation for that function. And we see this has some slackness from the bound. And then we have our bound, which is even farther below that bound. But it seems that they're all lower bounding in the right direction, as our theorem says. And interestingly, when we get to high learning rates, the bounds actually become much closer, and we can show that this seems that it actually becomes a very tight characterization of the predictor. Okay, so far we talked about univariate neural network, meaning functions that are from R to R, but we're more interested maybe in multivariate inputs, neural networks. And in that case, can we say something about the implicit bias? So this is expression we had for univariate neural networks. And now the generalization of this is something which seems similar. So instead of a second derivative of the function, a scalar function, we get the Laplacian of the function, meaning the trace of the Hessian from the predictor. And again, we have the absolute value of this, and rho is some density, which is it can be calculated. It's defined as some transform, inverse Redon transform of some well-defined function, which again depends only on the data set. And this is smaller than 1 over the step size minus half. So we call this integral here the stability norm. We have different forms for this in the paper. This is one perhaps simple form. And just try to understand what's going on. So we have some function. This is a function, a 2D function here we have x1, x2. So it's piecewise linear because there are because it's made up of values. And if we take the Laplacian of this function, we get kind of line, which are delta functions on a line. And the data points here are in blue. And now we need to integrate those lines with this raw function, which we can visualize this raw function for this data here, and we get the stability norm. Okay, so we get a more complicated expression, but it's still useful. So what can we say? So first, it seems that again, that if we have a larger step size, we get a smoother predictor. Okay, so we can see this again in 2D, that small step size get wildly fluctuating predictors, which perfectly fit the data points, but have those sharp peaks and valleys. And if we increase the step sizes, become more calm and eventually much flatter. And other implication is we can show that stable, meaning shallow neural networks which converge to stable minima, are not universal approximators, in contrast to standard one hidden layer shallow networks, which are universal approximators. So what do I mean by that? Consider this function, this pyramid function. It's visualized here. And this function, it's easy to show. It can be represented by a 2 hidden layer ReLU network. When you train it with finite step size, you can show also it's a stable solution for this 2 hidden layer ReLU net. However, we can show that this function has infinite stability norm, meaning with 1 hidden layer, we cannot approximate it. If we're trying to converge with any finite step size, we'll not be able to converge this to a stable minimum. So it seems this depth separation between 1 hidden layer and 2 hidden layer using stability. So what can we say? What can a stable shallow neural network can approximate? Well, if they can't approximate this function, so it turns out, and there are more details in the paper, that you can approximate sufficiently smooth functions. Specifically, they have a bounded type of a weighted Sobolev norm. Okay, so those functions you can approximate using a stable one inner layer neural network. Okay, so to summarize this part, second part, SGD converges to stable minima, and stable minima, due to that, and use this property to show the stable minima become flatter as the step size increase. That means become flatter in predictor space, and they are flatter in function space. Sorry, in parameter space, and this parameter space flatness corresponds to smoother functions in predictor space. Okay, so that's very nice, but can this lead also to better generalization? So empirically, if we check this, so what we look exactly, we do this first numerically, of course. So here's a simple example in MNIST where we show our bounds are actually quite tight. This is our purple bound is our final bound. We see it bounds the sharpness and the 2 over the learning rate. And we get that as we increase the learning rate here, this is a specific setting we chose with high initialization, so we get bad performance at small learning rate. However, when we increase the learning rate, we get a much better performance. Okay, so it seems that this learning rate effect can actually improve generalization in this case. But can we say something theoretically about generalization? So for neural networks, it's a bit tricky at this point. So I'll go quickly about the work. We did this on a linear diagonal neural network, showing how implicit step size is affecting generalization. This is joint work with Moore, Spiegel-Naxon, Kaviar Vachindran, Nati Cerebro, and myself. So what is a deep linear diagonal model, or a deep linear diagonal neural network? So this is just a model. It's a linear predictor, x times b, where the weight matrix is parameterized by these parameters w to the power of d. And we usually have w plus and w minus, so you can represent both positive and negative numbers even when d is even. So what we show for this specific model, if we use we assume we converge to stable minima using a SGD, then we can show this type of expression, this norm on the predictor is bounded by 2 over and the learning rate with this constant, d squared. So what does this expression means? It means that we have a bounded weighted 2 of d times d minus 1 over d norm. Okay, so as we change the depth, this we'll get a different norm. Specifically for d equal 2, and if we assume that the mean of the data is non-zero, meaning we have a non-centered data, this gives us some bounded weighted L1 norm. And this is kind of similar to the rich regime, which was discussed in previous papers, which is different from the kernel regime. So you can't describe this minimum L1 solutions using a kernel. So it's a different regime which was considered rich and can get us good generalization in at least this model in sparse regression setting. And this was kind of an analog for the rich regime in neural network. We get better generalization when they're far away from the kernel regime. So specifically, we examined this sparse regression problem with X sample from this Gaussian, non-centered Gaussian distribution. Y is some k-sparse predictor operating on this each data point. And as we examine the generalization, the test loss, and we change the different initialization scales and the learning rate. So if we look at the smallest learning rate, this is the top curve here, we see that for very small initialization, we get good generalization, small test loss. This was shown that for gradient flow, exactly we have this exact result. We minimize the L1 norm for vanishing initialization scales. And however, for large initialization scales, we minimize the L2 norm of the predictor, and we get, in this case, in sparse regression setting, we get not so good generalization. However, in this setting, we show that when we increase the learning rate, we get the other lines here, which become more and more lower, meaning we improve the generalization until with a sufficient large learning rate, we get close to the L1 solution, meaning a good generalization. And specifically, we can show that we can get low population loss in this sparse regression setting if we have a sufficient number of samples, which is K, meaning the number of sparseness, time polylog D over delta. And this is some probability one minus delta. So as long as mu, the data is not non-center, meaning mu is not 0, and D equals 2, we get generalization with similar to kind of L1 regression setting. Okay, so that's it. Thank you very much. I'll be happy to hear any questions if you have.
Hi, thanks for the great talk. How high can the learning rate go then?
In which model?
So you have a lower bound, which is the second derivative integral.
Yeah.
How high can you keep increasing the learning rate to keep getting better?
Yeah.
Performance?
So until you get to the flattest possible minimum, right? There's no infinite number of you can't get like infinite flatness, right? So eventually you'll get some minimum, which is the flattest possible, and then you can't increase the learning rate anymore because you won't have any stable minimum to converge to.
Is there some sense in which how this depends on the architecture?
I guess it does, but I don't know how. Like, sounds like it may be a difficult question, but interesting question.
Just a sec, we have one more.
Thanks for your nice talk. I wanted to ask about the activation function. So your talk was about ReLU, and I'm wondering where in your analysis you use ReLU, or does your analysis really apply for any activation function?
Well, I guess you can use ReLU or leaky ReLU, but
like, are you using homogeneity somewhere in your argument, or?
So it's in the in the proof when you prove this bound here, you need to use a specific. You just rewrite the specific form of the Hessian with the ReLU, and then we bound it because of use the form of the ReLU to. If it was the ReLU, I think it would be at least not using our technique.
So, like, if I wanted to do this for tanh, would the same thing hold? Just this formula would become a little bit different?
I don't know. I don't know exactly how to do this for tanh.
So there is something specifically about ReLU that you need?
ReLU or leaky ReLU, yes, for this.
Is it possible to describe what it is that you're using, or like what's the essential thing that you need for your analysis to work?
It's just something that in the form of the Hessian that you get those indicator functions from the ReLU, and then you can use them to do those averages of the data.
Okay.
I think it's harder to do this because then you would get something which is okay. So in the end, you want to get something which depends on the predictor, but for ReLU, the predictor is it has like the second derivative of the predictor is just a sum of the delta functions times the weights, like W1, W2 times the delta function. That very simple form does not hold for other types of.
Okay, that's very helpful. And related question, the part that was co-authored with Greg, where you have this omega of F, if you take tanh, does that omega of F become a single point and you no longer have this ambiguity?
Tanh, I think with tanh, there's this, it's an odd function. So you have this ambiguity of plus minus 1, right? You can multiply the output.
Yeah, but that won't change the flatness, right, of the...
No, it's not change of flatness, just different minima of the same parameterization. So there is ambiguity in the, so you're talking about the univariate case or the multivariate
Like in
case?
any case, is it the case that if you move away from ReLU, then you no longer have this implementation ambiguity?
Okay, you have this, yes, because of them, if you homogeneity ambiguity, I think there's another ambiguity I'm trying to remember. Because you can switch, like, you can have different, okay, so you can have like several ReLU together in the same point, right? Division exactly the same, so how many, right, the same function you can implement it using like 2 values on the same point, or what,
I see.
right? You can decide how many values you assign to each kink.
Yeah. Okay, thank you.
You're welcome.
Yeah, just 1 second.
I was wondering what this analysis say about how we decay the learning rate over time. So should we decay it and then suddenly increase it so that we hopefully settle down on a stable minimum? And secondly, this bound was for a particular lambda, right? So if we have a schedule for lambda or a decaying schedule, can we have a similar bound for the eigenvalues? Or
Sorry, can you repeat the second question? I didn't follow.
so the bound that you have, this is for a particular learning rate, right?
Yeah, this is the analysis I showed you is for a constant learning rate. Yes.
Yeah, so I was wondering if that can be extended to a schedule of learning rate where we either increase lambda over epochs or decrease the learning rate.
Yeah, so we analyze here not the dynamics, but the minima we converge to. So this is the step size required for the minima to be stable. So I'm not sure exactly how to, what would the schedule here mean? Like, how do you define the stability of the minimum with schedule? Mm-hmm. So empirically, there's some work, I think there was a Gilmer that showed that if you use, for example, cosine decreasing schedule, then eventually you converge to this, the decrease of the learning rate in the end, it doesn't change much your sharpness. Okay. You're still staying close to this high learning rate sharp minima. It does. It's an interesting question. How far will you go? Like if you do for a long time, very small learning rate, you would probably go away again if you do SGD, I guess. But if you do sufficiently fast decreasing learning rate, then the cosine, I guess you would stay close. So I guess again it depends on the types of if you use SGD or GD. It's a very interesting question, but I don't think it can be answered directly with the analysis here. You need to consider the dynamics.
Okay, thank you.
You're welcome.
Really great talk. I have a couple of questions. The first one is pretty much the same one that was just asked. So suppose I wanted to use this result to set the step size. And so the analysis is made for a constant step size. And this gives me an upper bound of the largest step size that I can choose. But to compute that upper bound, I need to know F, but I'm actually learning F. So how do I use it in practice? And I guess connected to the scheduling question, I could use it because I have a current guess of F, and I could use that to select the current eta and then keep changing it. So So therefore, two entangled questions. How do I select eta, given that I don't know f in the eta constant regime? And doesn't that immediately lead to a schedule given the current estimate of f?
I see. So you're saying you should try to estimate f currently, and if you're not satisfied with the flatness, you should try to increase it, and something like this, right? And trying to follow your suggestion.
Yes, I'm saying that this gives you a formula to compute the upper bound on what eta should be, and to compute that upper bound, you need to know f, but you don't.
You need to know f. Yes. So you have f is your your function, the predictor of your neural network currently. So you have it, I guess.
But that is changing with the parameter, no? Or not?
Yeah, it's changing, of course. But like your current f, if you're currently at the minima, your current f will determine whether this minima is stable or not. So you can use
exactly,
this
that's the problem, that I don't know the true f at which this quantity is true. So how can I use it to set the learning rate? How can I use this result to set the learning rate?
So I guess if you assume you're close to minima, it should be an approximation of the true f, right? If you're far away, it's not very useful.
My other question was about the first part of the talk on continual learning. I think you said that you may not be able to prevent catastrophic forgetting if you just present one task at a time in a fixed deterministic order. However, if you do the cycles or if you do a randomized selection, then you can prevent. I was curious as to exactly, can you explain the intuition as to why the fixed order, I cannot prevent catastrophic forgetting, but as soon as I randomize the order, I solve the problem. It sounds like mysterious as to why that would be the case.
Yes. Yes. So let's look at the specific example we had. Oops, sorry. Okay. So that was the worst case example where if we don't do anything, like just look at somebody give you a set of tasks and give you this task, and then it's bad, where you will have catastrophic forgetting. So what happens here in this task? Initially you get the black lines are tasks which are huddled together. They're close, very near each other on the circle. So each time you project to the next task, you're going on the tangent direction, right? On the surface of the circle. You're not contracting toward the teacher. And that's the problem. You're constructing, so you're like gliding away until the end, and you don't really contract a lot. But even worse, you construct it in this way that forgetting the sum of all those residual is actually arbitrarily bad to go to one. However, if you take this example and you randomize the order, then this will collapse, right? So, for example, you first start from here, and then you go to one of the examples in the end, you'll project quite far, right? You'll do quite a strong contraction, right? From, let's say, if you do from the first task to the last task, then you'll immediately go to the teacher. There will be zero forgetting. You learn perfectly the teacher here, right? If you do something in the middle, you'll just be much faster. So this kind of breaks this carefully constructed example, and when we show, this is generally a good way to break such issues and prevent forgetting in the worst case.
And my last thing is primarily a comment, and it's probably a literature that you might be very unfamiliar with, but in the 80s or so, in the controls community, there was a lot of research about how do I identify or learn a system, and the question of persistence of excitations of the inputs was postulated as a criteria. In the 2000s, this was extended to switch systems, where you go with one dynamical system, then another, so akin to the idea of multiple tasks. And then the question of how quickly do I need to switch from one to the other came about. And this notion of persistence of excitation, that I needed to do a schedule where I visit all the systems sufficiently often was sort of the basic criteria in order to be able to learn all of the systems together. So I am postulating that there might be some connections with that, and that might allow it to extend it to the dynamic setting and more complex systems.
Yeah, I think it's an interesting analogy. Yeah, thanks. I'll think about it.
We have time for one more question.
I just wanted to ask if there are similar theoretical results, speaking of the second part of the talk, but not about the learning rate, but about the batch size, if we have some results on the implicit bias of it.
Okay, so for stability, it's, I guess, it's problematic, right? Here we just use the fact it's a necessary condition for SGD, so our condition does not depend on the batch size. So it's true for any batch size, because that's why it's a bound. So the question is, maybe you're far from the bound because this becomes like not tight in SGD. So the question is, what is the thing that you're are about? Like if you have some edge of stability for SGD that you're sitting on, I think there was some recent paper suggesting you have some something which like depend on the product of the Hessian and the direction of the variance in SGD. I forgot exactly how they called it. Which just suggested some other thing and showed empirically that actually you sit on the edge of stability on this quantity, not on this lambda max. So maybe you can analyze this quantity using similar results and get how the batch size is affecting from it. So I didn't do it if you want, but that could be a nice idea.
Okay, thanks.
Okay, so let's thank Daniel again. We have a coffee break till 11, and then we'll reconvene with Courtney's talk. Thanks again, Daniel, for joining us.
Thank you very much.
guessing that that's him? Like, I don't know. Yeah, so that seems cool. But you're saying that, like, it's, like, impossible to talk to him. He's just, like... I mean, I've definitely seen people like that, and it seems like a miserable way to live. Okay, so we'll have like at least 10 minutes for talks, questions at the end. Oh, that's true. That's true. Okay. Great to see everyone. So I'm very excited for our next talk. It's going to be given by Courtney Paquette. She's on the faculty at McGill University and also holds a prestigious CFAR Canada AI chair at Mila. She's previously worked both in academia at Lehigh University and the University of Waterloo and in industry at Google Brain. And we're so happy that she's joining us today to share with us some new results that advance our understanding of the role of stochasticity in optimization algorithms, including providing, in some settings, exact solutions describing the dynamics. I also want to, on behalf of Courtney, encourage questions before, during, after the talk. She's a great speaker, and we can have, she's here in person, we can have an interactive, informal. Okay, so, please.
Perfect. Thank you. Oh, back online. All right. Well, thank you first of all, to the organizers for inviting me here today. I'm excited. So today I'm going to talk to you about a culmination of this research work that I've been doing over the past 3 years. It started at Google Brain, and it's continued while I was at McGill, or I'm at McGill. I work with a bunch of great collaborators. So these are the people who I been collaborating with on this project. So Elliot, Jeffrey, and Ben are older. So Jeffrey and Ben are both at Google Brain. And then I had 2 graduate students, Kiwan and Andrew. Okay. So I'm from the optimization side, optimization theory side. So I thought I would start with explaining sort of the challenges that I see in optimization for machine learning right now. And the biggest challenge out there, at least in my opinion, is that there's a very large discrepancy between what is actually happening in the theory of optimization and what is actually happening in practice. Basically, practitioners seem to just ignore everything that theoreticians say. It might not be true, but it feels like it from the theory side. On the other hand, theoreticians will be like, okay, here's this great algorithm. Here, I'm going to prove convergence for it. And then they do plots like this in their paper, where you do runs of SGDs, or runs of an algorithm. So those are the gray lines. And your result is sort of the blue line. That's the theory line. And then what they say is, hey, it works so much better in practice than in theory, and we leave it at that. And I'm being very generous here by putting the theory at least close to what is happening in practice. Usually they're like not even on the same plot. Okay, so, and the problem is we just kind of, as theoreticians, we just say, hey, that's what happens in practice, and we leave it. No, that's not a great answer to this question. So the goal in this talk essentially is trying to bridge this gap. So why do we see this so much? Well, one thing for me, at least, of why I see this is that the recent push in optimization theory for machine learning has been to remove assumptions. Okay, so now we're working in the space of non-smooth, non-convex problems. At that point, it's every possible function that you could ever get, okay? So that's a little bit too general in some sense. There's some other complications with machine learning problems with optimization. One of them is that machine learning people don't really care about convergence. What they actually care about is some sort of other metric that they measure, okay? But optimization theory has always been about how fast you get to the optimum. But now they say, we don't really care about the optimum. What we actually care about is how well it does on something other, okay? This confuses optimizers because it's like, you told us this is the function you wanted, and yet you don't actually want that function. Okay, so there's some problems there. So, like I said, the goal of this talk is to somehow bridge this gap between theory and practice. So if there's anything you get out of this, it's hopefully this picture. So what is the idea? The idea here in this talk is I'm going to work on a very simple problem, just the least squares. Not deep at all, okay? Just minimizing ax equals b. And what I want to do is, using stochastic gradient descent, I want to be able to actually predict the exact training dynamics of SGD without ever actually running SGD, okay? I'm not going to run it, right? What am I allowed to use? Well, because I'm doing the least squares, I'm going to be allowed to use things about the spectrum of my Hessian, the targets, and the initialization. So just from the spectrum and the initialization, I can tell you at any iteration of SGD what it will be without running it. Okay, usually there's a, that's amazing. You're telling me I don't have to run anything. Okay, and so that's what this picture is saying. So here I'm plotting, I'm actually doing a random features on real data CFAR, okay? So here's the spectrum of that. And on the right here, what you're seeing is a plot of runs of different SGDs where I'm varying the number of samples. Okay, so the squiggly lines, of course, are SGD. And what you see is that there's a smooth curve which goes through the center of those. That's my prediction. It's my prediction of the training dynamics of SGD. That is not an average. That is literally, without running it, I can tell you what that curve is. Okay? Okay, so what should we possibly start to make? You can't do this, right? For a generic problem with minimal assumptions, you just can't produce a training dynamic. So why can I do it, and what sort of additional assumptions do I need to make about my machine learning problem? Well, first I'm just going to be solving a large sum, so I'm just sum of f sub i's. And the assumption I'm going to make is that I'm high dimensional. So what this means is that I don't just have a large number of samples, I also have a large number of features. So the n number of samples is big, but also the d, the space for which I'm minimizing my parameters over, is also quite large. Now, the other thing I'm going to assume is I'm actually going to be working in the proportional case. Okay, so what this means is that I'm going to assume that the ratio of number of samples to features, so the n over d, are at least polynomially related. Okay. Now, why is this important? Well, if you actually plot over time state-of-the-art models, looking at the number of parameters, so that's the d, that will be the x-axis, versus training data versus the n on the y-axis, and you look at these various models that have run, you can actually see that this proportionality case is really actually what is happening in practice. That the state-of-the-art models actually have both features and samples large. Okay. What this also tells you is that you are not in classical statistics settings. Classical statistics would tell you that you fix your dimension of your feature space and you let the number of samples get big. That's not actually what is happening in the machine learning models. Okay, so why does this high dimensionality make any difference? Well, the reason is that inputs which generate worst case complexity, which is typically how you analyze algorithms, actually can be really, really far from sort of the typical run of the data set. Okay? So if we want to imposed through sort of high dimensionality, we need to make some additional assumptions that can only be realizable in the high dimensional sense. And the typical way you do this is we're going to steal ideas from random matrix theory and high dimensional probability. And that is you put a probability distribution on the inputs. Okay? So the inputs being your data, your targets, and your initialization. Now, as a quick remark, we will show that the results that I'm going to present will be holding for deterministic design. So there will be deterministic algorithms which satisfy this, but we're going to show this for first random things, and then show that those random things all satisfy very deterministic conditions. Okay? So what happens to SGD as you make the dimensions get large? So let's look at a least squares problem. Again, I'm minimizing AX equals B. And here I'm thinking of A being random, a random matrix, so like my data, and B being a random vector. And now I'm just going to run vanilla SGD, okay? And I'm going to allow my step size to change. Then as you make the size of your model grow, what you'll see is that the value, the loss function at an iterative SGD will actually concentrate around a deterministic function. This deterministic function you can actually analyze, okay? And it's completely determined by the spectrum of the Hessian. So that's what the plot is on the left here. So what I'm doing is I'm generating a random A, random B, running SGD, and plotting the training curve. And I'm doing that with n is equal to 64, but also fixing the d size. So the ratio n over d, number of features and samples is fixed. Okay? And what you see in the shaded region is the variance of those runs. Yeah? No, because this is least squares, so the spectrum of the Hessian is constant across time. So the derivative of this function is just or the Hessian of it is A transpose A, and it's just fixed across the time.
Right. So you're saying the spectrum of the Hessian is constant over time. So what you're saying is that you take a random mean, you do this run, and you're saying that from the time that you begin, you can like predict ahead of time what that.
Yes. Yes. Yeah. Yep. So again, the shaded regions are the variance across the runs, and the different colors, I'm just making the sizes get larger and larger and larger. And so what you can see is as I make the size of my matrix, in the proportional case, get larger and larger and larger, the variance across these runs is shrinking, and it's converging to this red line. And you can write down what that red line is. So why is this even possible? What is going on here? So we're going to steal ideas from random matrix theory, and the idea is that for many, many different classes of high-dimensional random matrices, they satisfy something called universality. So there are properties about the random matrices, okay, which are universal, which means that they don't really depend on lots of moments. They only depend on a few moments of the data. What you want to think about if you've never seen this before is these are the law of large numbers and central limit theorems for random matrices. Okay? And these will be about eigenvalues and eigenvectors. And in particular, the thing that we are going to use heavily in this talk is something called the delocalization of an eigenvector of the matrix H. This satisfies the universality property, which is that the eigenvectors tend not to align with coordinate axes. They tend not to concentrate. The classical example of this is if you take a matrix A, look at generate its entries being normally distributed. If you compute the eigenvectors of A transpose A, they would just lie uniformly on a sphere. It means they're not concentrated around any single coordinate axes. Okay? But this generalizes. Okay? Yeah. Yes. Yeah, so here's actually the conditions that you'll need explicitly about it in terms of the actual A. Okay, so if you rotate, you'll put the U into here. So here's what you actually have to assume, okay? So the assumptions explicitly will be that I have this proportionality between my feature and sample space. And then I'm going to satisfy this delocalization. So one way of quantifying delocalization is through resolvence of the matrix. So here omega is a contour which encloses, it's a contouring complex space, which encloses the eigenvalues of the resolvent, which is zi minus m inverse. I might have that with a minus sign wrong. Some people, okay, resolvents are always confusing if you put the minus sign or not. But it's I times z minus m inverse, okay? And here's how you can one way of quantifying delocalization. So like in the first one, it says that no off-diagonal entry of AA transpose is very large. So that's the idea. Intuitively, what this is essentially saying from a data point is that there's no one single data point, no single row, which is super important. That all the rows are somehow the same. Okay? There's not one which like determines the optimum. Okay? That's the intuition. Yeah. Yeah. Mm-hmm. Yeah, but it doesn't just happen for Gaussian. So it turns out that lots of, maybe my next little thing, lots and lots of random matrices satisfy those conditions. Okay, not just Gaussians. Gaussians is a classical example of it. So for instance, any sample covariance matrix satisfies it, provided that your covariance structure is on the feature side. So you sort of have independent data points that will satisfy it. Random features also satisfies it. So here you take a product of two random matrices and apply an activation function to it. Call activation function here, the activation is done point-wise, or entry-wise. That matrix A also satisfies these delocalization. Okay? And you can imagine in high dimensions for a lot of data sets, actually, my next slide, also have this property. So you might say, does this hold for real data? And it's really a little bit hard to check, but here's a plot sort of trying to illustrate this. So here I did it on image data, so this is like CFAR 10 and MNIST. And what I've done is I plotted for you the maximal entry of the resolvent on the off diagonal as the sample size grows. So I took like a subset of CFAR and grew it. And what you can see from the slopes is that they're all kind of going down as n gets large. Okay? That's sort of indicating that they're getting small. Yeah. Yeah. Oops. This one?
Yeah. So, what happens if your spectrum is sort of heavy-tailed?
You can have heavy-tailed spectrum. This is all about eigenvectors. So it doesn't actually, you can have a heavy tail in your spectrum, but the eigenvectors just can't be localized around coordinate axes.
Doesn't the left-hand side scale to the maximum eigenvalue?
What?
The left-hand side of the inequality doesn't scale.
So you want to, so.
I guess that there is a difference between the eigenvalue of the resultant versus the eigenvalue of A.
Yes. Yeah, that's correct. Yeah. The other thing to point out is that you also need some sort of delocalization property with the targets and the initialization also. Okay? It's also a thing. Yeah. It's because the alpha, if you want to prove some of these things, have these resolving conditions, the current random matrix assumption, the current random matrix theory only has it for this proportional polynomial case, okay? It most likely holds true, these resolving conditions, for any independent rows. Okay. But it hasn't been proven in random matrix theory for N and D going large, yeah. You just need it like, okay. You need them to exist in the limit. Okay, so, because I'm thinking of n and d both big, so I need them to exist. I want to point out one thing from this plot is that MNIST, if you just take the full MNIST, it does not satisfy my resolvent conditions. But if I take like 99% of the entries, it does. So it essentially says these are probably too harsh, like these are what we used in the proof, but this is probably not the right assumptions to be made. Like you could probably weaken these and still get a result, okay, for data sets, real data sets. What else do I need to assume? I'm just gonna assume that my initialization is bounded and that my targets are bounded across dimensions. The reason for this is that I'm varying dimensions here, so I don't want sort of my targets and my initialization growing in the dimension. The other thing, at least for the brief moment, is that I'm going to be considering a small batch setting. So this means that I'm just doing vanilla SGD. I'm just choosing uniformly at random a single index, okay, to do my updates. I'm also going to be allowed to reuse data points. Okay, I'm doing multi-pass SGD. The other thing about my step size, and the only thing I need to assume, is that it's a bounded continuous function. Okay, so it has to converge as t gets large to some fixed quantity.
Does it matter if you do SGD with replacement?
It does. This I have to do with replacement. I will do a batch in a second, but I don't have right now, and it's a great question if people are interested, to do this result using sort of a fixed permutation of your number index. Great question. Yeah. Yeah, go ahead. No, it's great. I'm happy for this. Yeah.
Was it just that a few data points are causing it?
Yeah, there's like just a very few outlier values that in the off diagonals, which are just really, really large. Yeah.
Do those examples look weird?
So I didn't look at the examples. It's a good question. I didn't look at them. It seems like you can remove them and do just as well, I think. But it's a good question. I didn't look, so maybe they are just really weird. So what is this exact function that it converges to? So here I'm going to let t be the number of passes through my data set. So I'm doing epochs here. And what you can show is that the loss evaluated at the iterative SGD will actually converge to this deterministic function psi as the dimension gets large. And this psi is just a solution to a simple Volterra equation. And you can write down explicitly what that Volterra equation is. It's a sum of two terms. One, which is the loss evaluated at gradient flow. And the second is actually what SGD noise is doing. If anyone asks you what SGD, choosing uniformly at random indices, that noise, it's given by that expression there. And you can see that the loss is appearing again on that side. So that's creating the Volterra part of it. All of these terms are just completely determined by the eigenvalues of the Hessian. Okay. So you can solve this Volterra equation if you've ever taken an ODEs course, or many years ago, maybe. You can actually solve this quite easily. Okay. I also want to point out there was a question in the previous talk about this. Because of this dynamics, you actually don't need the step size being small. The loss evaluated at the iterative of SGD will actually always converge to this deterministic function, even if SGD diverges. So if the deterministic function diverges or converges, SGD will diverge and converge. So what this means is you can actually get the edge of stability if you want for SGD, at least in the least squares case. The step size needs to be strictly less than twice over the average eigenvalue. Okay? Because you can analyze the dynamics exactly. You have deterministic dynamics. It turns out you can do this for more than just training loss. You can also do this for expected risk. So here, I'm looking at A and B being some new data point that I didn't train on. I'm going to evaluate it at the iterative SGD generated by this least squares. And again, what you see is that the expected risk evaluated at SGD will converge to a deterministic function, and you can write it down. This time it's going to piggyback on the loss. So what you get here is that the risk evaluated at gradient flow plus a term, which is the noise, but what you see instead of omega appearing on there is that you see the loss appearing. So the noise is scaling by the loss for the expected risk. Again, all of these functions are completely determined by the spectrum. So the kernel and the risk evaluated at gradient flow is just determined by the spectrum of the Hessian. Okay? You can immediately get some consequences that you've seen probably before. One is that because this is a noise term, it's a positive term, it always adds to your expected risk. So the expected risk of SGD is always greater than the expected risk of gradient flow for least squares. The noise never helps you. Okay? Moreover, yeah, go ahead.
Regarding the probability equation,
Yeah.
Yes, I would have expected, what is the probability that the screen was bigger than epsilon for an arbitrarily chosen epsilon, and then probably I want to have a capital T that grows with 1 over epsilon. So the question is then you have a constant, it depends on the C that I don't know what it is, and if C is small.
Yeah, so
Can you comment on the...
yeah, so this is a great question. Okay, so the thing is this has to do with, because I'm sending n and t, I'm sending n to infinity or d to infinity here. So there's a problem of setting time also to infinity of which order you take the limits in. This is fixing the amount of time, capital T, that you run and showing that as you send n and d, taking the limit first in n and d, then it concentrates. So technically on that side, this is a with high probability or with overwhelming probability result. Technically there's a constant in front of that d which depends on capital T. Okay.
And what does C depend on?
C is just, that you can take to be any C. It will be roughly 1/2. Yeah. It's actually 1/2 plus epsilon. I can't prove it is exactly 1/2, but 1/2 is the optimal one. That's like how the Gaussian scales. Yeah, great question. Any others? Thank you. I hope this is interesting to people. So, and then going along with this, I just want to show that you also get what you expect here, because if the loss is going to 0, then psi is going to 0, so you recover gradient flow. And also, if your step size is going to 0, then also that mixing term, the noise term, is 0, so you end up again in gradient flow. So in the limit, you always end up kind of in terms of gradient flow. So here I'm taking the limit as n go to infinity, and then the limit as t. It's a little bit funny thing here. Just to show you that this works, you can take real data, compute the spectrum. So here again, I'm using a random features model, and predict the training dynamics and predict the expected risk. So nice when those curves line up on top of each other. Yeah, they're the question. It's just, what it means is that you take just one index. So it's like 1 over n. Yeah, the fraction, sorry, I meant the fraction. The back fraction is going to 0. Sorry, it's like 1, sorry. Yeah.
So you've been trying to advocate that we don't need to solve the optimization problem to make all of these predictions, but we do need to solve the Volterra equation.
Yes.
And the first term of it is the evaluation of the loss on gradient flow.
Yes.
So I need to do gradient flow, which is running that.
Yes, okay. So in fact, this is always the optimizer, and I'm also an optimizer. I'm actually not really advocating that you don't do optimization, because then it would put me out of a job too. So I still think you should do optimization. The point I want to make about this is that if you now reduce it down to deterministic dynamics, you have an equation, you can get things like step size, because now you removed all of that hard randomness, which makes SGD annoying, and you can understand how does step size affect convergence, how does batch size affect convergence, and how does momentum parameters, any of those hyperparameters, actually affect your convergence. So it's being able not just to write down the dynamics, but also to analyze the dynamics. And Volterra's, you can do it. Yeah. Yes.
Again, the first term of the Volterra is the gradient flow, and I think that is for a given A.
Yes.
But the A is random, so isn't it the case that you have 1 omega t for each random choice of A and B?
You're right. So here it's like I'm actually, when I do this probability, I'm actually assuming that my A or my eigenvalues are fixed. The reasoning is that for real data, there doesn't seem to be a universality result for the eigenvalues. Like the eigenvalues seem to vary widely across data sets. So I want to make at least a statement about, given an eigenvalue distribution, what you would result in. Eigenvectors, on the other hand, do seem, at least for images, I don't know, maybe for other things, this is a good project, seem to sort of be delocalized. Like that seems to be an okay. It's, again, this idea that eventually, you know, not one data point is super important. And that's what it's really saying. Great questions. Okay. So I wanted to say why you can do all of this, and I'm probably going to run out of time, so hopefully I have a little bit. Give me a moment. So why does this all work? So the basic idea is that we created a new diffusion process, which we called homogenized SGD, okay? And the idea with homogenized SGD is that instead of sending step size to 0, which is typically how you create diffusions, you're instead going to send n to infinity. This is because I get to work in high dimensions. I can use that to discretize my space. Then what you show is actually that that this homogenized SGD is actually the high dimensional equivalent of SGD, meaning that if you take any quadratic statistic, you look at Q, that statistic, evaluated under SGD, it will concentrate around the Q evaluated at the solution to this diffusion. Then it turns out that this diffusion is actually quite nice, and it will concentrate around its mean easily. That's the trick. Okay? Yeah. Yes. Yes. So exactly, in the convex setting, that's exactly what happens. And you can actually just directly prove that through Jensen's inequality. Yeah, for a convex objective. Deep, non-convex, all bets are off, okay? I do want to also mention, so why is this different than the diffusion process you typically see for SGD? So this is the stochastic modified one. So here you have this drift, and here you have this term in front of the Brownian motion, which is actually usually the covariance of the increments of SGD. Okay, so how does this compare with homogenized SGD? Okay, I'm writing them down side by side. The difference is in the term, in the matrix term in front of the Brownian motion. The diffusion coefficient is not the covariance of the increments of SGD. Okay? So what is it, and why does this work? Because you would think that it's the increments of SGD. That one should solve it. Okay, so if you write these two things down, here's the diffusion coefficient for homogenized SGD, and here's the SGD increment. Okay, if you let n get very, very large, then you can drop off one of the terms. Now, even still, these two things are not the same. So why does this work? Okay, it works because what you actually are evaluating everything on is not in norm. So you're not actually going to compare the norm of that matrix to the norm of that other matrix. So the difference in norms of matrix, okay. The norm of that matrix minus that matrix is not the thing that matters, okay? So what does matter is that you're actually caring more about what happens as you hit quadratics forms of it. So we're actually looking at what happens as you take X transpose times the matrix X. That will actually concentrate around the SGD increment. That's actually what is close. That's a trick which is used in random matrix theory for proving things about determinantal equivalences. Hopefully some people know that's out here. So again, these two matrices are not close in norm, but they are close when you hit random vectors on either side. Okay? But why does that matter? Well, what matters is that, well, if you use the other one instead, because that's sort of what you're measuring your statistics based off of on quadratic things, this actually becomes solvable, this diffusion process. So in the case of least squares, your Hessian is a fixed matrix, okay? And if we look now at this in terms of the singular vector basis, the only thing which is causing a coupling across my different stochastic things is actually the loss, this loss of xt. So now this loss of xt is just a single statistic, which is combining all the coordinates. Okay? So if the loss is concentrating, then this diffusion process completely decouples, and you can solve it. And then the loss would be easy to compute. So you can actually make this sort of weird argument that as the loss is concentrating, the diffusion decouples, you can solve it and get the loss again. Rigorous, and showed the high dimensional equivalence. That's actually why it works. So this goes to the question now of why do we even care about the dynamics? And the reason is that we can also get information about parameter selection. So here I'm going to look now, I'm going to extend this all to stochastic gradient descent with momentum and batch. You can do it for any first order stochastic method. Okay? So I'm going to let zeta be the batch fraction, and delta and gamma, delta being my momentum and gamma being my step size. What we know is that when zeta goes to 0, SGD with momentum will converge to SGD. It's actually just the same dynamics. And when zeta is equal to 1, we know that there's a very specific choice of our step size for which we attain a faster rate over gradient descent. So the question has always been what actually happens in between? How does all these different parameters affect our convergence? So the first thing I want to show is that, in fact, you can get the exact same convergence result for this SGD with momentum with batches. So again, the loss at SGD with momentum will concentrate around a deterministic function. Any risk evaluated at SGD will also concentrate around a deterministic function. And you can write down those deterministic functions. Again, there will just be explicit functions of the eigenvalues of your Hessian. You can also figure out what the edge of stability is for this, because you know precisely when Volterra equations converge. There's theory on when do they converge, and so you can write down exactly when that happens. And that determines sort of step size parameters as a function of batch. Okay? So let's analyze this dynamics in more details. So again, we see that we have a Volterra equation, which is just broken into two terms. The first term is the loss evaluated at SGD plus momentum now, but with a step size which actually scales with the batch. Okay? And then we get the noise term. And the thing to note is let's let lambda be the rate that the one that we're really comfortable about, full batch gradient descent with momentum, decrease that. Okay? And what we'll see is that for some gamma and delta choices, what will happen is that this noise term will start to be the dominant thing in this dynamics. Like the noise, eventually, if you send gamma and delta large enough, the noise is the thing which you're actually like trying to solve. That slows you down the most. But because you have this exact dynamics, you can actually just plot for every batch, every gamma, and every delta, exactly what the convergence rate will be. It turns out it's the max of the convergence of the rate that gradient descent plus momentum goes down, plus the second term, which is called the Malthusian exponent. It comes from stochastic processes. You can plot this for every single one. So in the top picture, I'm going to show you how you do this. So I'm fixing the batch fraction. And in the first picture on the top row, I'm showing you what lambda looks like as a function. Okay, so I'm showing you how gamma and momentum parameters affect your convergence just for the gradient descent plus momentum with a batch. Then in the second, I'm showing you what this Malthusian exponent looks like. So it turns out for different gammas and deltas in the black region, there is no Malthusian exponent. It doesn't exist. It's like the noise doesn't matter. Then all of a sudden, the noise is important. And then what actually is affecting the convergence is taking the max of those two, which we see on the far right. And the line, the red line, is separating where you end up in sort of just pure gradient descent plus momentum, full batch, versus where the noise actually matters. It turns out the optimum generally occurs right on that line. So what this means is that as a function of gamma and momentum, your convergence is not a smooth function. It's continuous, but it has a jump. Okay? You can do this for various different batches, and this is what you see here. So on the far left, you see a 0.7 batch, a 0.5, and a 0.25. And you can also plot the optimal. I wanted to show you this so it's a little bit clearer. This is what it is for single batch SGD. So this is a plot of the convergence rate as a function of step. And so you can see that jump. There's like a special gamma choice where you switch over from looking like something like gradient descent to all of a sudden having something else which looks like the noise. And it makes that little quadratic thing. What looks like a quadratic, it's more complicated than a quadratic. Okay? Notice that the optimal step size is just always a little bit in the noise regime. You always want to produce a little bit of noise of SGD. So what can you do? You can now get optimal parameters. Again, because you have exact dynamics, you have equalities everywhere. There's no worry about inequalities. So the two things which are going to matter here is the average condition number, which is the average eigenvalue divided by the smallest, and the classical one. And so you can get almost optimal parameters as a function of your batch, okay, by choosing this. And that's just because you have equalities everywhere. You have the best inequality out there, equalities, okay? Now, if you look at this really carefully, you can actually see in the momentum parameter here that that's the only place where you see the batch fraction appear, okay? So what this means, and what you see in the delta, the momentum parameter, is that you get a rate of SGD and a rate of full batch gradient descent with momentum. So the idea here is that if you want to see acceleration like you're used to with momentum, if you choose a special batch, you'll actually cause delta to be the max, which is the gradient descent plus momentum. Hopefully, have I lost everyone? Sorry, it's a lot of stuff. Any questions? Maybe I should pause. Yeah. Yeah, you can do this for polynomial ones, or for linear rates also. So as the smallest eigenvalue. I just plotted this for the larger, the fixed one. Yeah. And it only depends on the small, I mean, it's like, because of how gradient descent depends on it linearly, and then it jumps over. Yeah. Any others? Yeah. You get average case for free because it's constant. It's worst case also in high dimensions, right? Everything is concentrating around some deterministic function. So even in the worst case, it's the deterministic function. But it is in some sense like an average, like a typical thing. If you you assume that your problems are high dimensional. Other questions? Have I lost? Everyone okay? Here are the optimal parameters of SGD with momentum. It's not 0.9. Sorry again to ruin everyone. It's not 0.9. It depends, as everyone would expect, on the average condition number versus the classic square root. So again, you can actually now choose the batch. Oops, there we go. Okay. So what I'm going to do here is I'm going to introduce something, what I call the implicit conditioning ratio, which is just the ratio of the average over the square root. And what you can show is that if your batch fraction is larger than this ICR, what you get is acceleration of stochastic gradient descent with momentum. You actually achieve acceleration. Yay, now we know. It has to do with the ratio of average and condition. For a small batch, I'm going to say is when my batch fraction is less than this ICR, and then you end up looking somewhat like SGD. It's scaling a little bit with the batch fraction, but it has roughly the same rate. Okay? And just to show you this, what this intuitively means is that there's like a batch saturation point, which is that if you add more to your batch, you're not gaining anything in speed. This is something that we all have exceeded, right? You don't actually need a batch to go to 1, batch fraction to go to 1, right, to see the acceleration. There's like a point where adding more to your batch doesn't really help you. And you can actually quantify it exactly and prove that it is exactly, there's a constant. You can look at the paper what the constant is, exactly at this point, this ICR. You can also run on data sets and actually see that this ICR kind of works. So it's, again, very nice. So what I'm plotting here is the last iterate. I run SGD plus momentum with the last iterate was like 50 iterations of it. I'm plotting f of x50. Okay, and then I'm just varying that with Dimford's batch fraction. And what you see, of course, is that eventually, adding more to your batch doesn't really help you because the function value stays the constant at that same thing, and so you always get the same. So that doesn't add more. And the ICR is exactly predicting that transition point. This is the thing that we all know about. You never actually needed to send batch to 1 to get acceleration, yet all of our proofs required it. And the reason they required it is because if you assume very little about your data sets and things, you just can't see it. There are data sets which require you to actually send your batch fraction to 1. Okay, but in high dimensions, we don't expect that. Okay? This also tells you when does SGD actually perform better than full batch momentum is just when the ICR is strictly less than 1. Something you can check involving the condition number and the average condition number. And you can actually see this. Okay, it takes a little bit of work, but you can use something like a least squares problem, put a distribution on your A, okay, so that you fix the smallest eigenvalue, but it allows you to vary easily a knob in the largest eigenvalue, so you can change the ICR. Okay? And so here I'm changing the ICR, so I'm making my ICR as I go across get larger, and again get larger. And momentum here is the up and down, okay? Gradient descent is that dashed line, sorry for these being small. And SGD is, in the first picture, is the best one, okay? And you can see as you make the ICR get larger and larger, eventually SGD with momentum will actually outperform SGD, okay? And it occurs roughly at 1. Again, there's a constant technically in front of it. You can do this on 2-layer neural networks, so now the Hessian is actually also changing. So this, you have to be a little bit careful. You have to change, how do you change like a knob to cause the ICR? So how do you change a little bit of your thing so that little parameters so that the largest and smallest eigenvalue and trace kind of change in a way that's predictable? But you can do this. Here I did with an activation function, which is beta. And the dashed lines are showing you how the ICR changes. So in the left picture on a 2-layer neural network, you can see that the ICR is actually changing over time because the Hessian is changing over time, so it's changing. But what you'll always see, at least on the left, is that the ICR for that the gradient descent with momentum ICR, these two things, and the ICR with SGD are always above 1. And as a result of that, momentum will actually outperform SGD. Then, by choosing that beta, here the ICRs for both SGD and gradient and momentum gradient descent are below 1, and so what you get is that SGD is actually outperforming. And that's just by changing the beta. That's the knob we use. Okay? And so I just wanted to end. I think I'm out of time. This is based on a lot of works, 2 of which will be at NeurIPS this year. So if you have more questions, you can come and see me at NeurIPS. And it's based off of a bunch of works that we've been doing in this area. So thank you so much. And I can take any questions. Yeah.
Can you do full batch GD analysis like this?
With a deterministic, yes. It's just not as interesting. So in that case, the averages, our worst case analysis basically matches the high dimensional. So high dimensional doesn't buy you anything. And that's true basically for all deterministic algorithms. It's only in the stochastic where it seems to buy you some more. Yeah, oh. Yeah.
On a realistic problem, like maybe the 2-layer random feature model,
Yeah.
how sensitive is the ICR to data structure, and how sensitive is it to kind of the choice of the nonlinearity?
Oh, it's it's really hard. Like there's so many different knobs you can turn that will affect it. It's actually really hard to just have like an easy one choice. This took a lot. I didn't actually do this one experiment. This is Jeffrey. Jeffrey was doing this experiment and he was like, it's so hard to figure out what, like, does the activation just change it? How does it change the ICR? Because it like changes everything, and architecture will affect it. For lots of architectures, it seems like the ICR doesn't change at all over time. For some architectures, the ICR changes a lot. It also seems to depend on the data, how much data you have. I don't actually know. It's a great question. I think this is something that is interesting to explore more also. Yeah.
Hello. Thanks for the very interesting talk. I'm curious, I guess I have a 2-part question. One is, could you briefly summarize on an intuitive level what the role of momentum is in this? Like what benefit does it have? And I'm also curious, can you think of other, like, maybe to be a bit more specific, like momentum plays a role in like classic optimization theories as like performing acceleration, but you could also imagine that it has another role of like smoothing out noise in the optimization, or you could come up with a few different possible mechanisms of what it's actually doing.
Yeah, it's a good question. I mean, like in the deterministic, we think of, it's the classic, it's a rolling ball down a hill kind of, you're somehow accelerating in that sense. It's a good question. I didn't explore a whole bunch of the effect of momentum is. You can try and do that basically by trying to understand the dynamics. So here you have what exactly the effect of momentum is on the noise at SGD. It's in this W. It's an explicit function. You can just write it down. So you could actually analyze the exact effect. By the way, you can do this. These results don't just hold for momentum. They hold for every sort of first-order stochastic algorithm. Okay, provided that your algorithm has the form that it's x0 plus something in the span of the gradients, previous gradients. That form, this idea always holds. Okay.
But sorry.
Go ahead.
Is what makes the optimal, like, is it related to this classic idea of somehow accelerating things, or what is?
It has to do with the kernel function. So it's this function that matters. Yeah, and that's what's determining how much noise you're adding, and also the effect. It also, this and this term are related to each other.
Thank you.
Yeah. Okay, there's lots of questions. Okay, sorry, go ahead. I don't know who's next. Oh, okay.
Yeah. Thanks. So this result is specific to Pollak's momentum, or what about Nesterov, for example, or like there are other types of momenti, or whatever you call those things?
It works completely. Okay, so everyone's asking about what these things are. So when you're doing on a least squares problem sorry, I'll do this over here. When you're working on a least squares problem in the deterministic, so full batch, everything, you can write down a formula for the dynamics, which is just a polynomial in the Hessian. So it just depends on the iterates just depend on a polynomial in the Hessian. Okay, this is similar to how you prove CG, okay? The idea of CG, conjugate gradient. That polynomial is what appears here and it affects your W here. So that's exactly all you replace if you change the different algorithms. So you would just take whatever the polynomial is for Nesterov, which you can write down. It will affect this quantity and it will affect here.
And you would have a similar kind of saturation phenomena and similar sort of behavior like what you showed in those graphs?
I haven't plotted Nesterov yet, but I think so, yeah.
Thank you.
Actually, I have, but okay. That's my master's student is finishing his thesis. That's his thesis project. It will be out soon on it.
Thank you for an interesting talk. So, I work on NLP, and I observe that Adam works like magic when compared to like SCD and SCD with momentum. So I'm curious if there is an analysis for Adam and when SCD or SCD with momentum sort of performs better than Adam, or why it performs like second order momentum.
Yeah, so in order, first of all, this framework doesn't work for Adam just simply because it's on sorry. This framework doesn't work very well for Adam just because it's on a least squares problem, so it doesn't really make sense to work with it. So in order to extend this, you need to essentially extend to another type of problem. So there's a lot of people, I think, in this room, I think a lot of interest in trying to extend these types of ideas to, say, a two-layer linear neural network anyway. There you might be able to actually start to analyze things like Adam. I mean, the first step is still to analyze the dynamics of SGD, and then you might be able to do the Adam stuff, okay? Good question.
Hey, thanks for the talk.
Yeah.
There's like, I was just wanting to get your comments. There's like proofs in the implicit bias literature of like convergence to exact points, and they replace these things with optimization statements. And they're all usually like some form of a composition of linear functions. Do you think you get a similar exact solution in that situation?
I can't, I don't know. I don't actually know. How about this? The dynamics get untractable very, very quickly for non-convex problems. There's a good research problem out there right now is there a simple non-convex optimization problem for which you can explicitly write down dynamics for? I think the closest, which I think people in this room, is something like matrix completion. Seems to be at least slightly tractable, okay? But there's just a problem, and that would be the first, something that's tractable that you can actually analyze that mimics a lot of these properties so that you can't do deep neural networks and try to do the dynamics. It's just impossible for it. But you like some simple model. So that's a good open question out there. What is a simple model, simple non-convex model that has certain properties? And then you can start to answer those questions.
But I guess for matrix completion, have people done Do you know of any closed form solutions there?
There's somebody in this room on here. Okay. You should talk to Renee. You can do gradient flow dynamics, or at least start to understand some of the gradient flow dynamics. SGD, you can imagine that it probably has some sort of similar structure where you have to first understand gradient flow because of the first term, and then you have the noise part.
I see. Thank you.
Yeah, so great talk. So I have a question about the kernel of the noise.
Sorry,
I have a question about the kernel of the covariance of the noise. So I guess it was a loss times session, roughly.
Yeah.
Is there a hope that a similar form can be more or less true for a more general model?
It's a great question. Also something that I think should be done, and also something I'm interested in. So if someone wants to do that, this is probably the true statement for convex, because you first need to say it's the square root, so it needs to be convex for that Hessian. The question is, if you do non-convex, what should you replace the Hessian with? Probably it's something to do with like an NGK kernel, something like that. I don't actually know the answer to that question, but that's my guess. You would want to replace it with something like that quantity.
A small follow-up. Can you also compute the noise for like label noise?
Yes, the label noise doesn't actually affect anything, because what it does is it appears, let me go back a second. It appears in that first term, the gradient flow term. It has almost no impact on the actual SGD noise. Like that's just, I know everyone always talks about noise and that, but it just actually is in the gradient flow.
It's counterintuitive.
It doesn't do, is it?
Okay, so
are we stopping?
I have some announcements.
Okay.
So lunch is going to be in the Great Hall. And then we'll return here for the afternoon talks. The speakers for the afternoon, the contributed talks, please.
What time is afternoon?
1:30. The speakers for the afternoon talks, please send your slides to the organizers. And let me just conclude by saying that this audience was fantastic. You guys really took the suggestion to heart to ask questions during the talk and after, and it made such a lively and lovely atmosphere. So Courtney will be at lunch, and let's continue the discussion there. What? Okay, and let's just thank Courtney again for such a great talk and for fostering such a lively discussion.
Please send your talks to this guy, Mikio. Contributed talks. He is responsible. Thank you.
are just filtering in.
Yeah.
Should we wait like 2 minutes?
I usually wait 2 to 4 minutes. I don't know
Okay.
what the protocol is at this conference.
Let's do that.
Okay. First time ever.
Wow.
Yeah. Good forcing function. Yeah. I hope it's not too embarrassing. Sabbatical. Although the company's still on there.
Oh my God, really?
Yeah, it's a startup. It's so
Wow, what's that like?
pretty hectic. Pretty stressful.
Really?
Ran out of money. Recession.
Wow.
It's very different than academia.
Is it like a lame duck session of Congress or something?
The company will officially dissolve December 31st.
Oh my God, really?
Yeah.
That's exciting.
Kind of, yeah. After you get over the 7 stages of grief, yeah, which I am over. Yeah, it is. It's kind of a first.
That's a different experience.
It is, yeah.
Oh, why don't I start?
Sure.
All right. So before I start the afternoon session, I have a personal request. So I tried my best and only made partial progress meeting the women that came for the conference. And I just want to say I'll stick around at the end of the conference today. I would be very happy if more women came down and introduced themselves and we meet each other. Okay, let me start the afternoon session. Yisong Yue is on the faculty at Caltech. He's worked at Disney Research, at Carnegie Mellon, and is currently working at Argo AI on self-driving technologies. Today, he'll share with us ideas about how to improve our understanding of deep learning by studying the internal structure of neural networks, and we're very excited to see what he's going to present now.
Thank you for the kind introduction, and thank you to the conference organizers for inviting me here. It's a real great pleasure to be at this conference. This is going to be the very first time I've given this talk, and I must thank the conference organizers for providing a great forcing function to make me create this talk. So today I'll be talking about how we can look at the internal structure of neural networks to help give guidance in how to control its inference and learning processes. So machine learning is transforming science. It was used to discover a structurally new antibiotic called halicin. It's used to dramatically improve the precision of CRISPR guide editing. It's used to dramatically improve the accuracy of protein folding. At Caltech, we've been using it to improve the quality of personalized exoskeletons in therapies for paraplegics. Machine learning is also transforming autonomous decision-making, for example, in playing games like Go. It's actually commercially deployed in, for instance, in Microsoft's Azure Personalizer, which is a machine learning approach, sort of like bandits and reinforcement learning, that helps small businesses personalize content recommendations. It's quite, I think, a very exciting commercial achievement. I actually worked on a project in collaboration with the Walt Disney Company on data-driven lip syncing, where given input audio, we automatically lip sync to any target character. So hopefully the audio works here.
Somewhere over the rainbow, way up high, and the dreams that you've dreamed of once in a lullaby.
So these types of tasks require keyframing the animation at very high temporal resolution, which is actually quite tedious for animation artists. It's not something that they find creative, and with machine learning approaches, we can actually just automate these processes away. Machine learning is also transforming creativity. So this is a person who used, I believe this was Stable Diffusion, to win an art competition in Idaho, I believe. And if you read the tagline of the URL of the news article, it says that artists are pissed. So it's quite remarkable. And so I think it's hard to overstate just the remarkable progress that these neural networks have made in terms of capabilities over the last several years compared to just, say, 5 or 10 years ago. And so it's worth, at this point, pausing to ask the question, what is actually happening, and how can we make it better in a rigorous way? So fundamentally, what is machine learning? Okay, I think it's a little bit of review, but just so we're on the same page. You have a large amount of data, I'll call it X. You use some sort of learning signal, I'll call it L of X. You put that into an optimization problem with a function class F. F is a neural network in this case, theta being the parameters, and we find a parameterization of the neural network that minimizes the loss function over the data. Pretty standard at this point. And of course, if you work on things like Stable Diffusion, you're very happy afterwards. However, from that sort of clean cartoon depiction of machine learning, the reality is that tuning these neural networks is very messy and hard. On the one hand, we have many different architectures. This is actually an extremely outdated screenshot from what's called the Neural Network Zoo from 2016 of different architecture types. There are many more now, including things like transformers. There's all these different hyperparameters and configurations you have to set when you want to run your optimizer, things like initialization, activation, loss, function, architecture, type, depth, width, dropout rate, so on and so forth. And then you get issues where you train for a while and then suddenly things collapse and you struggle to understand why, and after spending $1 million on training. And so people have, of course, observed this. I'm sure many of you have noticed this. And in fact, it gets so extreme that people start making memes and jokes out of it. For example, you get papers titled things like From Grad Student Descent to Automated Machine Learning. And you get papers like Hyperparameter Tuning Without Grad Students. And obviously, this is a bit tongue-in-cheek. These are actual papers. They're published at JMLR and NeurIPS. And I guess it just speaks to just how messy this process is. And so we're going to look at the optimization foundations of machine learning and start to understand sort of a little bit better what's going on. We're going to just start from the canonical foundation in view of machine learning optimization. So we have this very typical update rule, gradient descent, where you have your parameters, which I'll denote theta for the entirety of this talk. You have your gradient of your loss function with respect to those parameters. And then you have a learning rate, which is one of many tunable hyperparameters in the learning approach. And then you use this as an update rule, and then you sort of follow the gradient of the loss function until you hit some valley. Hopefully that's a really good valley, and then that you deploy your system. If we think about this from a theoretical standpoint, and I know I'm being a little bit sort of very simplistic here for this audience, but please bear with me. I want to keep it sort of high level right now. In theory, we would set this learning rate or step size using things like perturbation analysis, like what is the global Lipschitz constant of our function class, and also composed with our loss function. In practice, of course, we don't do that. We pick our learning rate using heuristics semi-arbitrarily, and if we change anything else about our learning setup, like batch norm or whatever, we may have to retune our learning rate completely. And this is part of why it's so messy. There are many, many parameters to tune, and here I'm just talking about the learning rate. So, I think it's instructive then to sort of think about, well, okay, let me go back one slide. One thing that's sort of limiting about this theory, or this simplistic theory, is that it's dependent on this notion of a global Lipschitz constant, a Lipschitz constant that bounds the perturbation analysis of this function class over the entire input domain of the function. And you can imagine that might be very coarse. And that's part of the reason why this kind of theory is not nuanced enough to be useful in practice. And so let's look inside a neural network. So this is just this is a neural network with 5 hidden layers. You have your input on the left, output on the right. For the entirety of this talk, the hidden layers are denoted by H. So here we, imagine we have capital N hidden layers, or hidden state outputs. The per layer functions that transform the previous hidden layer to the current hidden layer, I will denote F for the entirety of this talk. And then and each of those has parameters, and then the full function class is the composition of these Fs. One very popular example of a function is a linear with a ReLU, or rectified linear unit activation. And what that is, and the equation is on the left here, is you take the inner product of your parameters of that layer with the input hidden layer. And then if that linear dot product is positive, then you keep it as is. If it's negative, you zero it out. That's the entire function. And you compose this over many, many layers, many, many large width, and you get a deep neural network that's quite powerful in practice. So what's the intuition for why this is powerful? Well, the basic idea is that you're actually learning a sequence of transformations of the input representation. And as you learn this sequence of representations, each dimension of a hidden layer is kind of like a half-space mapping. And the goal is to learn a sequence so that the last layer of representations is somehow easy or good. And in this particular case, it separates a binary classification problem. So, okay, how do we sort of take this structure and try to start building a more nuanced theory to characterize what's happening inside a neural network? So idea one, per layer perturbation analysis. How does changing a single layer's function work under changing just that single layer's parameters? So in other words, we take a single layer, and we look at the parameters of a single layer, and we look at a perturbation of that single layer parameters, and we ask how the entire function might change because of that. If we can understand this well, one potential application may include things like depth and width invariant scaling of the learning rate. So that can, for example, substantially minimize the amount of tuning we need to do in the future. A second idea is, suppose there's a way to control the dynamics of the hidden layer transformations. So recall from this cartoon picture, we have this sequence of transformations of the hidden layers from sort of an initial representation to one that leads to a good prediction, or a loss minimizing representation, if you will. And so another goal might be, well, is there a way to control the sequence of hidden layer activations, H1 through Hn, so that it quickly and robustly converges to a representation that gives us zero loss or low loss? So those are the two ideas we'll be exploring in this presentation. So to summarize, in this talk, we'll be looking at two things. First, we're going to look at how to exploit the structure of neural networks to develop a more nuanced theory within a per-layer perturbation approach cast in what's a very general optimization framework called majorize-minimize. And it'll lead to a notion of trust region called deep relative trust. And then in the second half of this talk, we'll look at control theoretic shaping of neural ordinary differential equations. So let's start with the first half. So as a warm-up, let's just start from basics, from first-year calculus, we're going to do the Taylor expansion of the perturbation of our function with respect to the loss. So that's what I mean by L of theta plus delta theta. So this is just the Taylor expansion. Nothing too crazy going on here. And if we just take the linear approximation, the first order approximation of the Taylor approximation of the Taylor expansion, excuse me, we get something that looks like this at that point theta 0. It's just a tangent. Hopefully this is more or less review for everyone here. The linear approximation, to no surprise of everyone in this room, breaks down as the perturbation increases, right? It becomes a horrible approximation to this loss function as the perturbation increases in magnitude. And it's important, theoretically, then, to understand somehow the rate of this breakdown via some more nuanced perturbation analysis. And so let me first, next, summarize the majorize-minimize framework, which is a very, very general optimization framework. If you were at Francis Bach's talk yesterday, he talks about maximizing lower bounds being a very important design principle. This is really minimizing upper bounds. So it's kind of the same idea in sort of the 10,000-foot view. So the idea is you develop a majorization of the point you're currently at. And so that's this red line. It upper bounds the loss function everywhere, and it's tangent to the current iterate at that point. And then you minimize this loss function. So hopefully this majorization is somehow easy to optimize. And you minimize it, find its minimum, and then you get your new point, and then this process repeats. So this is the very general framework. The typical form of this looks like this. You want to find a delta theta, a perturbation of your current parameters, that minimizes this majorization. This majorization is represented as the order k Taylor approximation. For linear, it's k equals 1. And then some kind of upper bound on the rest. And so it should come as no surprise that this is a generalization of gradient descent. So if you want to pick the first order Taylor approximation plus this sort of quadratic majorization upper bound of the rest, you get gradient descent. If you pick first order Taylor approximation with some other kind of divergence known as a Bregman divergence, of which the quadratic is a special case, you get this more general notion of gradient descent called mirror descent. And then you could do other things as well. You could do a second order approximation. You get things like cubic regularized Newton. Okay, and just as one aside, although I won't talk about it too much, many of you will know that there's this duality between the majorization and truss regions. So why is this gradient descent? This particular, the minimal solution to this iterate of majorization has a closed form solution that is exactly this equation here. And that implies the gradient descent update rule with this particular learning rate. And that's why this is gradient descent. Of course, it is analogous by duality theory to to minimizing this linear approximation to your loss function subject to the perturbation, excuse me, this should be a delta theta, not a theta, being no greater than some constant. And this is known as a truss region. This is the region that I trust my linear approximation to the loss function. And so these are, of course, duals to each other. And theoretical guidance, now that we've laid all this out, you set the learning rate via theoretical guidance from perturbation sensitivity like the Lipschitz constant. So now that's how this all sort of comes full circle. Okay, so this is the general framework. And now we're going to ask the question, how do we define a majorization that exploits the neural network internal structure? And this is work led by Jeremy Bernstein, who's here. He's a former PhD student of mine about to start a postdoc at MIT. And Kevin Huang, who was a former undergrad of mine, who recently started as a PhD student at the University of Washington. So the first key idea is, I've said this before, per layer perturbation analysis. We perturb an entire layer's worth of parameters, but just that layer, not the other parameters, and we analyze its perturbation of the final output. So here's a thought experiment. If we vary only the nth layer, what is the Lipschitz constant over the entire function as we vary the nth layer? It actually depends on the value of the parameters of the other layers. If the other parameters are larger, as we value the parameters of the nth layer, the perturbation to the overall function is also larger. And so this gives you sort of a hint of why this global Lipschitz constant that upper bounds the Lipschitz perturbation, or the perturbation, if you will, of the entire function class everywhere might be a very coarse and loose characterization, and therefore not useful in guiding actual optimizer design. So we're gonna develop some architecture where perturbation bounds. This work is actually unpublished currently, although we'll be submitting it for peer review soon. You can find it in Jeremy Bernstein's PhD thesis, which I'll remind you all of later in this talk. So for L2 loss or squared loss, we have the first order Taylor approximation and the upper bound of the rest. We're going to just basically replace this upper bound of the rest with this two quantities. The first quantity is an overall perturbation sensitivity around the current parameterization theta. The second quantity characterizes the breakdown of the linear approximation. And Jeremy and Kevin developed an upper bound of both of these terms. And the key thing that I want you to get out of this, and it's probably too much to digest right now in this talk, is the thing in black in the bottom, is that there's this term which is the ratio of the size of the perturbation of the nth layer with the spectrum norm. Recall that each layer, the parameters of each layer is an entire matrix, weight matrix for every sort of edge from every hidden layer to every output hidden layer. It's a ratio of the spectral norm of the perturbation of that layer divided by the current magnitude of that layer. And so this is sort of the key piece that we use to build these majorizations and analogously to define a trust region, which we call deep relative trust. And so now let's put it all together. We first derive a majorization of the error, which is what I just derived in the last slide. We plug in an architecture perturbation bound, which is also something I just showed you in the last slide. And then we minimize this majorization, so this whole thing, with the upper bounds replaced. We minimize this whole majorization to obtain our iterative optimization algorithm. That's the high level idea. Some desiderata and caveats. The bound I showed you currently is only for deep linear networks, so the nonlinearities are removed in the analysis. Nonetheless, this is the first ever bound of its type, even for deep linear networks. The issue is that for something like a rectified linear unit, activation unit, the issue is the kink, right, where it goes from flat to linear. Analyzing that kink is hard. So, but if you're never close to that kink, then this theory also applies as well. And figuring out how to get this theory to also apply to that kink is future work. Nonetheless, we feel confident that this can still offer strong guidance for designing optimizers for large, deep neural networks. Yes, question?
So I see that the F has disappeared in the bounds. So is it captured inside the C?
Yes, there is a dependence on F inside the C, yeah. In particular, you need to upper bound the neural net overall output.
I was asking because, so when you say you minimize the upper bounds, C will be held constant?
So the question is, if the C constants include include a dependence on F, how do you actually minimize this? So I will answer this with the next point I'm going to make, which is that this majorization has no known closed form solution, and therefore it is hard to optimize. One of the reasons why people chose the other majorizations, like squared potential functions and Bregman divergences, or some Bregman divergences, is in part because the iterate has a closed form solution, and therefore the majorization, you could solve for the optimal update under that majorization in closed form. However, you can make the argument that majorization is actually not a good characterization of deep learning, and therefore the optimal update is not that great either. So what we're doing instead is we're going to give you a more nuanced majorization characterization of deep learning, but we're going to fail to give you the optimal update rule. We're going to only give you an approximate update rule. That's the difference. Right, so solving for the optimal perturbation is itself an optimization problem. So here's our optimizer. Here's the punchline of the first half of this talk. You could look at the full derivation in theorem 6.2 in Jeremy's thesis. The key idea to get a closed form solution is to have a restriction where we enforce the relative update in terms of spectral norm of the parameters. We enforce the relative update of each layer to be the same relative magnitude update. So this leads to a suboptimal but closed form update rule. And it's as follows. We have the parameters of the nth layer. We scale inversely by the total depth of the neural network. We scale inverse square root by the dimensionality of the hidden layer that we're acting on. The update direction, the gradient direction is normalized, so it's a unit vector. And then we scale by the current magnitude of the current weights of that layer. So the basic idea is you tune this learning rate once for a small network, and then the step size, and you transfer it to wider and deeper networks using this update rule. Because we have a formula for how this transfers to wider networks. We have a formula for how this transfers to deeper networks. And if you've read the work of Greg Yang and his collaborators at Microsoft Research on mu parameterization, this is highly related, and in some sense can be viewed as a generalization because mu parameterization only studies width scaling, not depth scaling. Okay, so how does this work in practice? Here's one experiment where on the vertical, we're looking at neural networks of different depth. The different color codings are different widths. So this is fully connected multilayer perceptrons. And then the x-axis is the learning rate, and the y-axis is loss. Lower is better. What I want you to notice in this figure is that the optimal learning rate is more or less in the same. You just set the learning rate once, and then you scale by depth and width according to the formula, and you more or less get good, stable learning behavior without having to retune your optimizer. And this pattern is consistent over the different epochs of learning. So in other words, with this update rule, the same learning rate is near optimal across depth and width scaling. Here's another case study for training very, very deep neural networks. So these neural networks are fully connected and are, in general, very, very hard to train. What people do in practice is they make the neural network architecture easier to train by adding things like normalization layers and adding things like skip connections. But if we just said, what if we just wanted to train a gigantic, fully connected, no skip layer, no bells and whistles, deep neural network, say 50 layers? Is that even possible? Well, it turns out SGD and Atom just break down. They can't really train beyond like 25 layers in this type of architecture. Whereas if you use this kind of scaling rule, optimizer scaling rule, yeah, it's not perfect, but you can see that we've made some progress in uncovering the principles of architecture-aware optimizer design. Because we've actually trained non-trivial networks that actually learn something, even at 50 layers. Okay, let's take a step back. So there are different ways of designing optimizers. Right now, we've talked about looking at the perturbation analysis per layer. And then you could think of that as sort of a weight matrix, right? Each layer has this weight matrix. You can also do per neuron. So one output node of a hidden layer. So you can do a perturbation analysis per neuron. You could do a perturbation analysis per synapse. One connection, one weight connection between one hidden unit from the previous layer to one hidden unit to the output layer. You can do it all three. And in fact, we did. So per layer, the first algorithm we designed, which we called Fromage, was really the first foray into this. It was work really that was sort of the spark plug for Jeremy Bernstein's PhD thesis. We also studied per neuron, which we call Neuro. This is joint work between Yang Liu, who was a PhD student at Caltech, and Jeremy. And so it looks at how to constrain looks at how to do perturbation analysis and update rules per neuron. So all the input weights, the fan-in weights to a single neuron of a hidden unit. And there are also other properties you can add to this in this particular construction of if you're looking at the architecture in this way. For example, you can constrain the per neuron weight norms to be balanced. From there, you can look at the actual structure of the architecture and see connections to batch norm that's implicit in this construction, and also connections to generalization. You can do it per synapse. This is joint work between Jeremy and Jiawei Zhao, who was a PhD student at Caltech. And you could also, in this case, study things like, okay, what if we constrain the weights to be non-negative? Then that leads to this multiplicative update rule, which if you sort of look at it, has interesting mathematical connections to actual biological synapses. So you get this entire sort of portfolio of different ways to study perturbation analyses, and these are all valid. Actually, the beauty of neural networks is that their structure is so rich. There's many different ways to abstractly think about understanding that structure. And these are only 3. I'm sure there are others to be found as well. Okay, so just to summarize the first half of this talk, we looked at architecture-aware perturbation bounds. We framed them within the framework, this very general framework called majorize, minimize. And from there, we developed these perturbation bounds that we can use to develop a majorization. And this allows us to develop an optimizer where you tune this learning rate once, and then you could transfer to neural networks of larger width and larger depth. This work is, if you're interested in understanding this work better, I strongly encourage you to check out Jeremy Bernstein's PhD thesis. It includes this and other work that he studied in terms of generalization as well. It's very self-contained, and I must say it's really a beautiful piece of work. It has a self-contained introduction to deep neural networks, function analysis theory, and then his actual contributions in optimization and generalization. So at this time, before I transition to the second half of the talk, I'll pause here if there are any quick questions. Yes?
So I think it was clear how you exploit the structure of the network to get a better perturbation analysis and how that leads to sort of a scaling of the gradient step. What wasn't clear to me is whether that allows you to get convergence rates and how would that compare to, say, not doing the scaling. So in a sense, I think you showed some experiments, but is there any theory that can justify the selection of the scaling?
So the question is there a convergence rate? And the answer is not yet. We focused first on understanding how the nuance of how different perturbation analyses affect the overall function as you scale width and depth. And that allows you to get a better handle on things like width and depth scaling, but it does not actually directly address overall convergence rates. So we have not actually studied that. It's, of course, a great direction for future work. Yes, question?
Yeah, so what I'm curious about is why does this framework allow for this stability of the optimal hyperparameter when you scale things up? Why does this work better as compared to I'm guessing gradient descent?
So the question is, perhaps in this particular figure, why does this work and why does gradient descent and atom don't work? And the answer, my intuition, and of course, if you want a more in-depth answer, you can talk to Jeremy, who's in the audience. My intuition is as follows. As you scale the depth of the network, the Lipschitz constant becomes really hard to control, right? And the Lipschitz constant, the appropriate Lipschitz constants might vary from layer to layer. And our update rule actually directly accounts for that. And Atom and SGD do not. If you want a more in-depth answer, you can talk to Jeremy. So, okay, I think I will move on to the second half of my talk. In the second half of my talk, we'll be talking about control theoretic shaping of neural ODEs. So recall idea 2 that I talked about in the very beginning of this talk, which is thinking about how we can control the sequence of hidden layer activations so that it quickly and robustly converges to low loss. This is sort of a high-level intuition, and now we're going to make it concrete. So as a warm-up, I'm going to redraw neural networks using block diagrams because they're easy to work with in the second half of the talk because the neural networks are going to get a little bit more complicated. So, but the intuition is the same. You have the input. You have an input layer function that converts the inputs to a hidden layer. You have hidden states. You have hidden layer functions. You have an output layer function, and then you have your output. So it's the same intuition, just a slightly different way of depicting neural nets. And now we're going to move on to ResNets, or residual networks. So how do ResNets work? You have, you have your hidden layer functions that actually, the important equation is the middle one on the bottom right. Your hidden layer functions do not directly just by themselves output the next hidden layer activations. They actually output a additive residual to the next hidden layer outputs. That's why they're called residual networks. That's the key difference. And ResNets are wildly popular function class used in practice. So, okay, let's pull out a constant factor delta from the function without loss of generality. So I'll call this delta. And we're gonna think of this as some kind of Euler integration step size. And in particular, if you take the limit of delta going to 0, you get what's called a continuous in depth, which gives us neuro ODEs. Where now, rather than having a finite set of discrete hidden layer activations, where each hidden layer is in an additive residual, you get basically a dynamical system where the instantaneous change in the hidden layer is described by this function. And that leads us to neuro ODEs. So in neuro ODEs, we have an input layer, at least the way I'm going to describe neuro ODEs. They have an input layer that maps your input x to this hidden state at time 0, h0. We have a continuum of hidden layers, also known as the dynamics of the neuro ODE, that basically operates on the instantaneous change of your hidden states h. And then we have an output layer that takes your hidden states, whatever they might be, and maps it to a prediction, y. So a few comments. If you actually want to run the forward pass, it requires running an ODE solve. You can actually evaluate the output at any time, right? I can evaluate the output at t equals 0.5, for example. You don't have to actually wait till you've run your ODE to the end to evaluate the output. You can actually evaluate this anytime. And this function class also includes things like continuous normalizing flows and many other classes of generative models. So it's actually a pretty popular function class. Okay, we're going to look at how to use control theory to shape the learning of neuro ODEs. Control theory is a much older field than learning, and it's been used to shape many types of dynamical systems, most commonly ODEs. And you can shape these dynamical systems to have properties such as stability, where the dynamics of the system stabilize to a point or a set. Things like safety or forward invariance, where the dynamics never leave some safe set. Things like adversarial robustness, where if you perturb the inputs, the dynamics still never sort of deviate too strongly from the optimal trajectory. These are all things that control theory has studied for decades. Why would you want to shape the dynamics of a neuro ODE? Here's a simple example. So here we have a 2D hidden state space where the red class is the correct class and the blue class is the incorrect class. What I'm showing you is different inference trajectories under perturbations. So the purple quiver plots are the dynamics of the neuro ODE hidden states, and the black dotted lines are the different trajectories from different perturbed initial conditions. And this particular neuro ODE is trained using standard backpropagation. And the thing I want you to notice is that this is unstable or not robust. Some of the trajectories with small perturbations to the input and initial condition give you the wrong answer. If you train a neuro ODE to be stable, such as our approach, which is led by Ivan, who's in the audience, then you get stability and stable fast convergence to the correct answer. Okay. So what dynamics can we shape? Okay, how do we actually go about shaping this? On the one hand, we can try to shape the full dynamics. This is perhaps too unwieldy. The dynamics can be high dimensional, perhaps too unwieldy. So let's try instead to shape a projection of the dynamics, in particular a one-dimensional projection of the dynamics. And to do so, we're going to define what's called a potential function, capital V. And we're going to make the obvious choice of capital V, which is the loss function. So the potential function at time, the value of the potential function at time t is the training loss at time, at time t of the ODE inference. So you can think of this as the dynamics of the training loss as we do the forward inference. And again, this is just a one-dimensional projection, so it should be easier to work with. The first key property we're going to look at is a property called exponential stability. The goal is to train a neuro ODE such that the potential function, which is this training loss, converges exponentially quickly to 0. In other words, the loss decreases exponentially fast. In order to ensure this, the key invariant we'll be looking at, in order to guarantee this, is this contraction condition. What does this contraction condition say? Oh, there's a typo here. I'll change it. This should be an F, not a V. The contraction condition says that the rate of change of my potential function should be proportional to the value of my potential function. This is a standard property of exponential functions. The derivative of an exponential function is the value of the exponential function.
The term in the middle should be h dot.
I'm sorry?
The term.
This should be an F. It was a typo. Yeah. I'm sorry?
What is that?
F is the dynamics of your ODE.
Yeah, that's what I said, h dot. Because h dot is.
Sure, yes, yes. The benefits of this is that you get fast convergence and robustness if you can achieve this. So here's exponential convergence in action, if you can actually train a neural network to satisfy this property. So this is our approach, which is we call it LeoNet. Compared against a neuro ODE, the x-axis is inference time, and the y-axis is cross-entropy loss. The lower is better. And you can see empirically we achieved exponential convergence, where the training loss goes to 0 exponentially quickly. Okay. Now let's dig into how we measure progress via this contraction condition. So here I'm visualizing a 2-dimensional neuro ODE hidden state. I'll explain this plot. The blue are the regions of the state space where this contraction condition is satisfied in this particular instantiation. And the red is the region where the contraction condition is not satisfied. So the green is just showing one trajectory. So starting from that initial condition, how does the ODE flow? So a violation happens when the contraction condition is not satisfied. And then satisfaction is when the contraction condition is satisfied. I'm sorry, there's another typo. I will fix these things before I give it to everyone for publicly. And so if this contraction condition is satisfied everywhere in the state space, then you get exponential stability. This is just kind of a basic mathematical fact. And that leads us to the Lyapunov loss, which is one of Ivan's main inventions. So first we start with the pointwise Lyapunov loss, which basically says for a single input pair, xy, and any point in my hidden state space, h, I'm going to define this loss function that's like a hinge-like loss, which says if my contraction condition is violated, then the right-hand side of this max operator is going to be positive. If the contraction condition is violated, then the right-hand side of the max operator is going to be negative, and I'm going to floor it at 0, because I don't care. I don't care if it's contracted even faster. I just don't want it to contract slower than my desired contraction rate. So this is my training loss function for any xy pair at any single state h. And then the actual Lyapunov loss is just the expectation over all my training pairs, and then the integral of this pointwise Lyapunov loss over the interval of integration. If you achieve 0 Lyapunov loss everywhere, or almost everywhere, it directly implies exponential stability. And so the goal now is to train your neuro ODE to achieve 0 Lyapunov loss. Yes, there's a question.
Yes. I'm a little bit lost by the following. So typically, you would posit a particular Lyapunov function and then try to prove the inequality. And as part of that, you would derive the value of k. If, on the other hand, you simply posit the existence of a k, but then there isn't a k, then what would happen?
So the question,
You don't know the value of k, you could put the wrong k.
yeah, so the question is, typically, in these types of Lyapunov analysis, you first posit a Lyapunov function and prove that a potential function, and prove that it is a Lyapunov function for a dynamical system. Here we're asserting a potential function and trying to figure out whether or not the dynamical system satisfies the Lyapunov condition. It looks almost like the reverse way of designing things. Is that sort of a summary of your question? Yeah. I will, if you can hang on to that question, I'll answer it in a few slides. So with this Lyapunov function, here's the LeoNet framework. First, you interpret the training loss as this potential function. You instantiate the Lyapunov loss, or the pointwise Lyapunov loss, which measures at a single state the violation of this contraction condition. And then you optimize for this Lyapunov loss everywhere in your state space and make sure, and therefore get zero Lyapunov loss everywhere. At a high level, that's the idea. There are some optimization considerations, which some of you may have noticed. Evaluating this integral exactly is hard, really hard. So what we do instead, at least one simple thing you can do instead, is sample. For example, uniform Monte Carlo sampling, which means I sample XYH uniformly at random, and then I backprop from that sample on the pointwise Lyapunov loss. I choose a random XYH. I check with whether this pointwise Lyapunov condition is satisfied at that point. If it is not, that induces a backprop gradient on my neuro ODE. If it is satisfied, then I move on. So this is the approximation. There are other approximations as well, but this one is the simplest to describe. Some benefits of sampling. One really nice benefit is that it avoids running the forward pass ODE solve during backprop, which can get expensive. Since the goal is to minimize the Lyapunov loss everywhere, achieving this Lyapunov loss under a different measure, such as the uniform measure, if it achieves zero loss, it also implies that we're going to achieve zero Lyapunov loss under the original measure. So, to a certain extent, this seems to be fine as long as we're sampling in a good way. And I should just mention that the similar idea of avoiding the ODE solve and just sampling states is also used in training various generative models that based on ODEs, such as score-based generative models and Moser flows. So this idea is coming up over and over again, this principle of sampling and avoiding an ODE solve to backprop. So to answer the previous question, we're going to talk about connections to control theory. So first, let me start with a definition. A potential function V is considered an exponentially stabilizing control Lyapunov function for a controllable ODE if for all states H in some compact set at capital H, this particular condition is satisfied. And this condition is equivalent to the Lyapunov loss. And then in this case, we actually think of theta as the controller of the dynamical system. So that's the interpretation. So this basically says, can we find a controller theta that makes V a control Lyapunov function for this dynamical system? So this perhaps answers the previous question of how this is connected to previous Lyapunov theory. We're actually trying to find a controller that establishes the connection. That's the interpretation. Of course, in classic control, F has also uncontrollable dynamics in addition to the controllable dynamics, and theta is typically fairly low dimensional. Whereas here, there's a connection now between controllability and learnability, right? Now the question we're asking is, can we find a theta that achieves zero Lyapunov loss? And in learning, F is fully controllable and typically highly overparameterized. Yes, question?
The definition there is that for all H there exists a theta, or the other way around, there exists a theta for all H?
So the more flexible answer is, for all H, for any given H, I can find a theta. But you could also pick just this, but it also suffices if you can just find a single theta that is true, that is simultaneously true for all H. And that is typically possible when theta is overparameterized. But that's the situation you're in. Correct, yeah. Okay, so a few comments. So, and extensions. So typically, when you talk about stabilization and stuff like that, you talk about stabilizing to just a single point, a stabilization point. these ideas can actually be extended to stabilizing to sets rather than points. So for example, under adversarial perturbations, we can still stabilize to some region of low loss. And moreover, these sets need not be convex. We can think about optimizing not just one condition, one of these invariant conditions, but we can actually think about optimizing multiple combinations of them as well. And I'll give one example later at the very end of this talk. And then there are other types of invariances that fall into this family of invariances. For example, forward invariance, which basically says, I want my dynamics to never leave this quote unquote safe set. So let's quickly just run through these really quickly, and then I'll conclude my talk. First, let's talk about adversarial robustness. So in adversarial robustness, the adversary perturbs the inputs to try to confuse the classifier. So I add a little perturbation to the input. I'll call it epsilon. And then the classifier is adversarially robust if it can still make a correct prediction under bounded perturbations. So here's a simple 3-class example where the corners are the sort of perfect confidence in a given class, and this is sort of a cartoon depiction of the hidden states. And if you can get your hidden states to the top triangle, that corresponds to predicting the correct class. Even if you don't get your hidden states to that top corner, if you're in this correct region defined by this top trapezoid shaped thing, you will still end up outputting the correct class because it's the more confident class, but you just don't have perfect confidence. So as long as you get your dynamics into this correct region, you're still going to make a correct prediction. So the goal then is to have the dynamics of your ODE end up in this correct prediction region, even under adversarial perturbation to the inputs. And the way we sort of think about guaranteeing this is using this concept called Lyapunov level sets. So we have this potential function that has a specific geometric shape, which is this, this sort of V-shaped structure. And the Lyapunov level set basically says it's everywhere in the state space where the Lyapunov potential function has a value lower than some number. And forward invariance basically in this case states that the state space will always stay inside a sublevel set of the Lyapunov function. And this is satisfied for if you have sufficiently fast contraction, where over bar epsilon is the upper bound on the adversary. And so there's a lot of machine learning to actually get this to work in practice, including having an algorithm that actually certifies that this contraction property is satisfied, and if it's not certified, to sample more training data from that location. I'm not going to go into the details. That part of the work was really led by Yuja, who is also in the audience. And I just want to just sort of say one thing, which is, for CFAR10, which is a pretty challenging data set for adversarial robustness, this approach gets a certified robustness of 42% accuracy, which is certified. And the previous best certification result for these continuous depth neuro-ODE type models was 7%. So this is a significant lift for certified robustness of neuro-ODEs. And I believe it is state of the art for neuro-ODEs. Okay, the last thing I'm going to talk about is control barrier functions. So the basic idea with control barrier functions is that you never want your dynamics to leave some quote-unquote safe set. And this is defined by another potential function, I'll call it capital gamma, the sort of upside down V, being greater than 0. So the safe set is defined that way. And then the way you sort of enforce a local per state condition to sort of enforce this invariance everywhere, globally everywhere, is using this equation. And the only thing I want you to take away from this is that it is structurally identical to the Lyapunov contraction condition. And therefore, if you want to define properties of your neuro-ODE that can be formulated using these set invariants, you can optimize using the same machinery I just described. And in fact, we've done that. So this is joint work by Ivan and Noel, who is a PhD student in mechanical engineering at Caltech, where we learn a neuro-ODE policy to satisfy a composition, multiple barrier function certificates. And once you satisfy those barrier conditions, it actually implies indefinite walking, in this case of a bipedal robot. So here are two of, I think, between 5 and 7 of the barrier functions on an invariance conditions of the torsal angle never leaving some safe set and the swing of the foot never leaving some safe set. And once you train a neuro ODE and you sample the whole policy space to satisfy these barrier conditions, which have the same mathematical structure as the Lyapunov conditions, you can achieve guaranteed indefinite walking. Okay, so just to summarize, in the second part of this talk, I talked about control theoretic shaping of neuro ODEs. We looked at how we can interpret training loss functions in machine learning as potential functions. And we use them to shape the neuro ODEs to satisfy the Lyapunov condition of these potential functions. We get a myriad of interesting properties, including exponential convergence. And we could also get safety guarantees expressed in this way that can actually be realized on real autonomous systems. To conclude, I think taking a step back from the specifics that we talked about, I hope that I've convinced you that there's interesting work on the path towards a more structured, aware theory of deep learning. Neural networks are not arbitrary black box functions, and analyzing the structure carefully can lead to a more nuanced theory. Of course, this theory is incomplete, and there's a lot more work to be done. And moreover, by analyzing the structure, we can unlock new connections. And in particular, we talked about connections within the per-layer perturbation analysis to things like generalization and possibly even biological neural networks. You'll have to read the papers for the details. And then in the control theory side, of course, connections to nonlinear control theory. Finally, I'd like to thank my collaborators, especially the students in the top row, who of course did all the work. And the references are here. Thank you for your attention. Question, yes.
Something that I've just observed in my own experience is that when you train neural ODEs, they can sometimes solve a problem in the transients of dynamics. So is employing this what we call DeepMath, is that a way to make sure that it's solving problems using like asymptotic fixed points, or it's kind of moving away from transients?
I see. So the question, So the question is, sometimes in training neuro ODEs, it seems like the solution. Let me rephrase it this way. It seems like you train in a way such that if you integrate beyond, if you train to find a solution at t equals 1, and then you integrate to t equals 1.1, you're screwed somehow, right? And yes, that is part of the fragility of direct backpropagation, because it gives you exactly what you're optimizing for, no more, no less. When you train using things like Lyapunov loss, you get much more global structure in the dynamics, and you can integrate beyond t equals 1 and still get good answers. Question, yes.
So I guess I have two questions. The first one is just, so what part of this, do you need this continuous time limit? Can you think about the same things just in discrete time?
So the question is about whether or not you can reason about this continuous time limit of neuro ODEs in discrete time, and the answer is yes. There is a discrete time Lyapunov function. It's in the paper.
Oh, okay. Yeah. Is there an advantage to the continuous time? Or
is there an advantage to continuous time? So I am not an expert in control theory. I would invite you to ask Ivan, who's here. My rough take is that continuous time is just mathematically much easier to work with.
Okay, and the second question is just, so you mentioned that you have to do this like Monte Carlo sampling, and one of the things you have to sample over is like the hidden state space. So isn't that like a very high dimensional, like is there like a cursive dimensionality issue?
So the question is about whether or not sampling the state space suffers some cursive dimensionality. The answer is, of course, yes. Nonetheless, they have worked for things like score-based generative models, which use the same trick, just for optimizing the score function rather than the Lyapunov condition. So the Lyapunov condition you could think of as an inequality of a per-state property. The score-based generative model that optimizes for the score is actually an equality. But otherwise, mathematically, they're actually the same in terms of how they're structured. and that's scaled, right? Of course, it's expensive. But maybe a more nuanced answer to your question is that yes. And so part of certifying the forward invariance of these things requires adaptive sampling. Certain parts of the state space, you don't need to sample so aggressively because they're easy to satisfy. Other parts are harder, so you want to sample more densely. I don't have time to talk about the details, but if you're interested, you can check out this paper.
Thanks.
Yeah. I guess more apropos to your work, could you talk about maybe more of the practical applications for CV, CNNs, stuff like that?
I'm sorry, I don't even know where you are. Oh, okay. Sorry, I was too busy looking for you. What was the question again?
Yeah, I was just saying more apropos to your regular work. Could you talk a bit about perhaps more of the practical applications for CV, CNNs, things like that?
Right. So more practical work. Yeah. So I guess I don't have slides for this. Are you referring to the first half or the second half of the talk?
More of the first half, yeah.
Practical applications. So the most obvious practical application is width and depth scaling. So the biggest, if you talk to people like Google Brain, OpenAI, et cetera, they'll tell you, you just do hyperparameter sweeps, have some confidence that their hyperparameters can scale up to a larger neural net, then scale up. If it doesn't transfer, do another hyperparameter sweep. And that's part of why it's so expensive. And so the most immediate answer to your question is that this can help, significantly reduce that cost because we can do width and depth scaling, for example. Yeah. Actually, one interesting thing that I forgot to mention is that when training this neuro ODE on this bipedal robot, the training process was actually pretty hard. And the only algorithm we got to actually train this thing was the work I talked about in the first half of the talk. SGD and Atom actually didn't work. And in fact, Ivan was at risk of missing the deadline for the conference until he tried Jeremy's algorithm, and then it worked.
Yeah, thanks.
Hello. So you mentioned certified robustness for the neural ODs. You didn't go into the details of how you do certified robustness, but on the slide you had formal verification listed. So for normal, standard feed-forward networks, it is known that formal verification for anything beyond MNIST is just extremely, extremely time-consuming, and that's why people don't do it. What is the state in neural ODs? So is it time consuming, or are there any differences from standard ways we do formal verification?
Okay, so the currently standard ways to certify robustness in feed-forward neural networks or convolutional neural networks are based on things like if you're probabilistic, things like randomized smoothing. If you want to be deterministic, like SDP relaxations, maybe those interval propagation bounds and stuff like that, and they can get very expensive. Yeah. The nice thing about control theory is that if you can establish exponential convergence, you get a version of adversarial robustness as a corollary. Of course, establishing exponential convergence for any arbitrary neural network function class may be hard. So there's work to do there, and maybe it's impossible. There's some fundamental barrier there where you just can't be applied. But at least for neuro ODEs, if you can establish it, you get adversarial robustness for free.
I see. And when you say for free, you mean in the L2 sense?
I mean, if you can train a neuro ODE that with a contraction condition that is sufficiently fast, you get adversarial robustness as a corollary. This may not be possible. It may not be the right way to frame any problem because it may not be applicable. It definitely is applicable for neuro ODEs, and if you can train this with this at this sufficiently fast contraction, then you get it for free.
Thank you.
Thank you.
Oh wait. So, is it supposed to show up? Oh. I think this is just not. Should I do it again?
You hit present and it's not working?
Oh, okay.
Okay.
Now it's good.
Okay, so can you hear me? Can you hear me? Oh, okay. So welcome to the first contributed talk of the afternoon. So please, we're gonna start, so please take a seat. The first talk is by Salma Tarmoun from Johns Hopkins University, and she's gonna talk about the dynamics of gradient flow.
Thank you. Hello, everyone. So I'll be talking about the dynamics of gradient flow in overparameterized linear models. And this is joint work with Guy França, Benjamin Heffley, and René Vidal. So as you might all know, in deep learning, we're typically working with neural networks that are highly over-parameterized, meaning that they have many more learning weights compared to the training examples. This leads to problems that are highly underdetermined with many possible solutions that all fit the data perfectly. And in practice, we use variance of gradient descent to find one of these solutions. So although this works pretty well in practice, there are still a lot of mysteries regarding the behavior of these gradient descent algorithms. And mainly, we were wondering what the effect of overparameterization is on the learning dynamics. So in recent years, there has been an extensive body of work trying to answer this question. Some have suggested that perhaps overparameterization promotes generalization, which is what is typically referred to as implicit bias or implicit regularization, while others suggest that perhaps overparameterization accelerates convergence, and that is what is referred to as implicit acceleration. The caveat, though, is that most of the existing analysis makes strong assumptions on the initialization. Namely, they require it to be either spectral, vanishingly small, or balanced. And I'll explain what those types of initializations are in the next slides. So our goal is to also analyze the dynamics of gradient flow, the continuous version of gradient descent, in two-layer linear networks, but under more general initializations. And we will show that, first of all, overparameterization results in conservation laws that constrain the dynamics to follow certain trajectories. And more importantly, because of these conservation laws, we get a convergence rate that depends on the initialization. So we will get this imbalanced quantity that I will define in future slides, as well as capturing the eigenspectrum of the data here. So to start, I will start with a very simple warm-up example, which is just considering this objective function, 1/2 of y minus x squared, that we're trying to minimize using gradient flow. So this is not at all interesting from a practical standpoint, but it will help us illustrate the effect of overparameterization. So we assume that y is a known scalar that we're trying to learn, and we're running gradient flow on x. So the dynamics are very simple. They're just captured by this differential equation here, x dot is equal to y minus x. We can solve it in closed form, and the convergence rate is simply e to the minus t. So what does it mean for us to overparameterize this problem? Well, it means to replace x with a product of two parameters, u and v. So it's almost as if we go from depth 1 to depth 2, sorry. And when we run gradient flow on u and v, we get these slightly more complicated dynamics. So we have two differential equations on u and v, and the question is, what is the solution to this problem, and more importantly, what is the convergence rate? So before we get into the solution, it's very important to first notice that this problem actually has a scaling symmetry, meaning that if we take any solution or any parameters u and v and multiply u by some non-zero scalar alpha and divide v by the same non-zero scalar, then we get another solution that corresponds to the same loss function. And for those who come from a physics background, we know that symmetries in general are related to conservation laws. So here the quantity that is conserved ends up being u squared minus v squared. And it is equal to its value at initialization, which we denote by lambda 0. We will refer to this quantity as the imbalance because it captures the imbalance between the weights. And so in terms of the trajectory, what this means is that if we look here at the plot, so we have u on the x-axis and v on the v-axis, and this red curve represents the critical points for our problem. So different values of lambda 0 of the imbalance at initialization will give us different hyperbolic trajectories. So for example, if we start here with an imbalance of 10, we will get this trajectory, and that'll tell us which point we'll converge to on the red curve. We do have this very special trajectory that is just a straight line, which corresponds to the balanced case. So that's when the imbalance is simply 0. So now the question that we're really interested in is, how does the product x, which is u times v, behave during gradient flow over U and V, because that's what we really want to compare to the non-overparameterized case. And it turns out that that's captured by this nonlinear differential equation now. So it's x dot is equal to y minus x times the square root of the first term is simply the imbalance at initialization that we saw in the previous slide. So that already relates it to the conservation laws, plus 4x squared. Luckily here we can solve it in closed form, which is this pretty complicated formula. And what's really interesting is that the rate of convergence ends up being a function of both the imbalance at initialization and the data, which is simply captured by the scalar y. So just to summarize what we've seen so far in this scalar case, so we started with this objective, just 1/2 of y minus x squared. We tried to overparameterize it. We saw how we went from this simple linear ODE to something that is nonlinear and that depends on the conservation law. The solution is obviously also going to be different. And for the rate of convergence, we went from something that is e to the minus t that does not capture anything about the initialization or the data to something that actually depends on both quantities. So now obviously we're not just interested in analyzing the scalar case, we want to see what happens for neural networks. And so the setup is that we're considering a 2-layer linear network with a squared loss. So the xi's and yi's are training data, and we use U and V, the weight matrices for this network. Both of them have a number of columns, k that is larger than the minimum between the input and output dimensions. So that ensures that we're not in a case where it's a low rank factorization, basically. And we make this assumption that the data is whitened, which is a common assumption, meaning that the input correlation matrix is equal to the identity. And this allows us to show that the problem is actually equivalent to a matrix factorization. So it's almost as if we're trying to factorize the input-output correlation matrix. And just to simplify the notation, we'll simply be replacing that with the matrix Y. So from now on, we'll just be factorizing the matrix Y. So again, we're looking at the dynamics of gradient flow applied on, first, a 1-layer model, which is very trivial. So it's just looking at the minimum of 1/2 of the squared Frobenius norm of y minus x. And we overparameterize that in 2 different ways. So the first one is a symmetric factorization, which corresponds to a 2-layer model with tied weights. And the second one is an asymmetric factorization. So in that case, we don't make any constraints on the weights. So this is very similar to the scalar analysis. We get sort of the same equation for gradient flow, so x dot is equal to y minus x. The solution also looks pretty much the same. And again, we get that convergence rate of e to the minus t. So first, we tried the symmetric factorization. So now we're running gradient flow on U, which gives us these dynamics for U. And once again, we're more interested in the product because that's what we want to compare to the non-overparameterized case. So we try to look at the dynamics of UU transpose. So they're given here by this quadratic equation. And what's really interesting about it is that it's actually a Riccati equation. And Riccati equations have been extensively studied in the control theory literature, so we can leverage some of those results to understand the dynamics here. One last thing to note is that because in this problem we have a symmetric factorization, the solution cannot be, it has to be positive semi-definite. So x can only converge to something that ideally is going to be the projection of y onto the positive semi-definite cone. So using the fact that we have that Riccati equation that describes the dynamics, we actually know how to solve that in closed form, so that gives us a solution for x that's given here. And from this, we can try to analyze and get a convergence rate. So first, we'll start with the case where we assume a spectral initialization. So what this means is that our initialization has the same eigenvectors as the data matrix. So if this is the eigen decomposition of our data matrix Y, then then the initialization has the same eigenvectors in its eigendecomposition. And when that happens, we have two interesting things. The first one is that the eigenvectors remain constant throughout the trajectory, so only the eigenvalues are changing. And so the dynamics actually reduce to scalar dynamics just on the eigenvalues. We can solve those dynamics in closed form, so we get a solution for each eigenvalue of the matrix X, so those are the sigma I of T. And what's interesting here is that each eigenvalue will converge at a rate that is e to the minus 4t times the absolute value of the corresponding eigenvalue of the data matrix Y. So basically, the larger the eigenvalue, the faster we learn it. And the global rate of convergence has to be determined by the smallest one. So it's obviously going to be e to the minus 4t times the smallest eigenvalue of the matrix Y. Why is this not moving? Oops. So now if we don't assume a spectral initialization, can we get a convergence rate? Well, the answer is actually yes. So for almost any initialization that is positive semi-definite, we get the same convergence rate of e to the minus 4t times the smallest eigenvalue of Y. And here, almost any initialization, obviously there are certain pathological cases where we cannot converge to the solution, but with almost surely, almost any initialization, we can get this convergence rate. So now we move on to the asymmetric factorization. So again, we're just generalizing the scalar case where, so instead of working with just scalars, we have the products of matrices. So the gradient flow dynamics look pretty much the same. In terms of the conservation law, so we had u squared minus v squared that was conserved before. And now it ends up being the u transpose u minus v transpose v that is conserved. So once again, we look at the case where we have a spectral initialization, meaning that our initialization has the same eigenvectors as the data matrix. And once again, in that case, the eigenvectors remain constant throughout the trajectory, and we are only learning the singular values. So we get scalar dynamics for each singular value, and here the solution, if you recall, is the same as the solution that we saw for the scalar case. So we can conclude from that for each singular value of x, we get a convergence rate of e to the minus t times this square root of, so the first term is going to be the ith eigenvalue of the imbalance matrix, and the second term is simply the ith singular value of the data matrix Y. And we have here this plot that shows this basically. So we're trying to factorize a 5 by 5 matrix using both the asymmetric factorization or just the trivial one-layer case. And we see that when the imbalance is small, so that's what we have on the left plot, then the largest eigenvalues are learned much faster than the smallest ones. And as we move to the right, so as we increase the imbalance, we start to see that even the small eigenvalues are learned faster. So now we can assume a non-spectral initialization. And recall that first, the imbalance matrix is this u transpose u minus v transpose v. And so here, in terms of the rate of convergence, we can show that if the imbalance is 0, so that's the balanced case, then the rate of convergence will only depend on the data matrix. So that's going to be e to the minus 2t times the sigma min, so the smallest singular value of y. We can also look at a case where it's not balanced. So in that case, we assume that the imbalance is homogeneous, meaning that it's simply a scaled identity, so that's going to capture the degree of imbalance between the weights. And the reason why we make this assumption is that the dynamics once again reduce to a Riccati equation. And the convergence rate ends up being e to the minus t times the square root of, so once again, the first term, the lambda 0, captures the imbalance at initialization, plus the second term that captures the smallest singular value of the data matrix. So to conclude, the goal of our work was to provide a precise characterization of the solutions of gradient flow for overparameterized two-layer models. The main takeaways are that conservation laws constrain the system to follow particular trajectories, and that they have really important role in terms of the convergence rate. So we saw that the convergence rate will in all of these cases depend on the imbalance at initialization due to this conservation law, and on the singular values of the data matrix. And more importantly, we did not make any assumptions of balanced or vanishingly small or even spectral initializations. Thank you.
Question for Simon, thank you.
Yes.
So this required whitening. Is there
Yes.
any possible way that you can remove that assumption? And I assume it affects the conservation law.
It does not affect the conservation law. It is possible to work with a non-whitened case. I don't think that we'll get the Riccati equation again, so we will not have something that is very, precise. Right. Mm-hmm.
If the covariance matrix of X is invertible, you can just, again, multiply it by that inverse.
So I think it hits it on both sides. So it's not just an inverse.
What happens in that case is, while you could no longer solve it in closed
Mm-hmm.
form, you can get a rate similar to what
Right,
was
yeah.
written there, and you go back to the rate.
Yeah, I guess.
Yeah, this.
So
Oops.
the one that is right at the beginning. The rate.
This is just slow. It's not following what I'm trying to show.
But effectively, you get the smallest and the largest eigenvalue of X transpose X would appear in the
Right.
in the rate.
Okay, because I'm curious because you need some sort of, okay, well, we can talk about it later. Why I'm interested in that question.
Okay.
I have a quick question.
Sure.
So, is it easy to derive what is the conservation law that you have for any invariance?
Well, in general, so are you talking about just the case of gradient flow or any algorithm?
Yeah, for any invariance that you may have in your architecture.
Right. So that sort of depends. If you can write a Lagrangian that is like, if you can use that framework, then you have all that theory to get a conservation law. If not, it might be slightly more difficult. Yeah. Mm-hmm.
So, this technique relied on you not having, sorry, the symmetry came from having the identity activation function, right? Is this technique possible to adapt to the case of nonlinear activation function, or is that out of the scope of this?
So analyzing the symmetries and conservation laws would still be possible if you have, for example, positively homogeneous activations. But being able to get a Riccati equation or any solutions in closed form, I think, would probably be very difficult.
But even without the Riccati equation,
Oh, yeah.
like if you wanted to use tanh, that's my go-to
Mhm.
guy. Do you expect that there are symmetries in the first place that you can leverage? Or is this something about homogeneous activation functions?
I think, yeah, sorry, go ahead.
I think it's still an open question whether there are these. If you have
Right.
continuous symmetries for tanh, then you could find a conservation. But if you don't, we still don't know that yet.
Yeah, I mean, it's a question of finding the symmetries in that case. Right, if they exist. Mhm. Yes.
Something about the convergence rate. So that's e to the minus t sigma minimum. So if you think of adaptive gradient methods, anagram, or actually starting point of those, that was also because different modes, different eigenmodes are converging at different rates. Have you thought about how this is going to get modified if you were using something like anagram, some adaptive gradient?
Mm. So I think that, yeah, depending on the algorithm, you might still get the same conservation laws, at least, the continuous time. How that translates to convergence rates, I would not know.
The interesting thing is, so I guess the adaptive gradient methods which try to make this flow of the modes isotropic in the mode space would probably bring all of these modes with different eigenvalues to the same rate.
Right.
But I think what is interesting is that in your final result, you don't have just sigma min, you also have the convergence, the conserved quantity.
Right, yeah.
So it would be interesting to see, is this something extra that
Mm-hmm.
you need to consider about how this system converges? Could that help you maybe design a modified version of these optimizers, these adaptive
Mm-hmm.
optimizers, that takes the conserved quantity into account, which comes from the initialization?
Yeah, that's a really interesting direction. We have not explored that, but yeah. Thank you.
Thanks again, Sandra.
Yeah.
Do you have HDMI entrance? Perfect. That should work.
Oh.
Great. I'm gonna set it up. Do you need to plug?
Oh no.
So our next speaker is Tomer Galanti from MIT, and he's going to talk about SGD noise and low rank bias in deep networks.
So hello everyone, my name is Tomer Galanti. I will talk about SGD noise and low rank bias in deep neural networks. Very happy to be here. This is a collaboration with Zachary Sigo, Aparna Gupta, and Tommaso Poggio. So before I jump into our work and all of that, I just want to give like a short overview of things that we're probably all familiar with. So in classical machine learning, we typically have this idea of the generalization behaves like a bias variance trade-off, where we have two extremes. On one side, we have underfitting. The model is unable to fit most of the training samples. And in the other side, we have overfitting, where the model is very large and is able to perfectly fit each one of the training samples, but does not generalize to new samples. And there is this idea that we want to explore this sweet spot between the two regimes, where the model is kind of balanced and is able to fit the data and to generalize to new samples as well. And typically, in order to control this trade-off, we used to use regularization. And the idea is, as we all know, is to limit the capacity of the model, typically by adding some constraints to regularize or force that the model would be low complexity. But in practice, we see that we can train big models that are larger than the data set and generalization still occurs even without or with very little amount of explicit regularization. And one of the hypotheses or the research directions in order to solve and to understand this phenomenon is the idea of implicit regularization. Essentially, that the idea is that the optimizer in a certain way induces a bias of low complexity when training neural networks. So essentially, without explicit regularization, the optimizer, let's say SGD, is selecting or favoring solutions that have low complexity. And certain papers suggested different notions of complexity and tried to show that in different regimes, these quantities are being minimized by like standard optimizers that we care about. So for example, for linear models, it is quite well known that gradient descent kind of implicitly minimizes the norm when we optimize least squares problems. And other papers showed that gradient descent converges to minimum nuclear norm solutions for for matrix factorization problems. And other papers looked at the regime of like linearly separable data and showed that we learn rank 1 matrices in that case for certain loss functions. So basically the idea is that different papers try to come up with different regimes and different complexity measures and try to show that in these regimes these measures are being minimized. And overall, what we would like to understand is why SGD is able to generalize well, even when we train without weight decay. And beyond that, maybe to understand how different hyperparameters are able to affect this implicit regularization, whether the batch size or the learning rate have crucial effects on the minimization of these quantities. So in this work, basically we focus on two inductive biases. The first one is the low rank bias. So whether the optimizer is implicitly minimizing the rank of the weight matrices that we learn. And the second thing is the inherent noise in SGD, whether it is able or unable to converge even if we train for infinitely many iterations. Okay, so we consider a very broad setting. We have SGD together with or without weight decay, and we also incorporate something we call weight normalization. The network may have many different kind of modules like residual connections and so on. But in this talk, I will just focus on standard multi-layer perceptrons. So we have like a product of weight matrices interlaced with ReLU activations. And we start by decomposing the network into two parts. We have the norm of the network, which is the product of the Frobenius norms of the weight matrices. And we have the normalized network, which is the same neural network, but the weight matrices are now normalized. Okay, so the first quantity, we call it rho, and the second one is GV. So V are the normalized matrices. Okay, so we would like to minimize the following objective. Okay, so we have a standard loss. This is like an average over losses. We have weight decay. Okay, so we have a regularization term over the norm rho. And we also have a constraint to enforce that the weights are normalized. So VK are normalized. Okay, so we have this disentanglement between the two. And to ensure that the weights are normalized, we have Lagrange multipliers to enforce that. And basically, in this regime, we optimize VKs and raw kind of independently. So they are trained together, but each one has its own step. And without going into too much detail, these are the gradients of each one of the terms that we consider here. And if we apply it for SGD, so we basically sample a batch in each iteration, and we can look at the steps for the specific batch that we consider. And it is obvious that if we take lambda, if we take the regularization to be 0, then we can just perfectly fit the data if, let's say, we consider MSE loss. But otherwise, the derivatives of the loss function with respect to the output could be 0. And in that case, basically, the gradients are going to be 0 across all batches. Okay, so we get convergence for free when we perfectly fit the data in the unregularized case. So we call this property strict convergence when the gradients are uniformly 0 across all batches. This is slightly different than the original idea of convergence where we have, when we consider a critical point. But just to understand whether we have noise, whether we always make steps, we talk about this idea of strict convergence. And this is a very simple lemma showing that if we apply weight decay, if we have non-zero regularization, any strict convergence point is going to be equivalent to 0. Okay, or the data lies on a one-dimensional space, which is unrealistic. Okay, so unless we just converge to 0, there is no convergence. So in practical settings, we just don't have convergence. So SGD strict convergence is impossible when incorporating regularization. But there is another question: what happens near convergence? Okay, whether we are able to see some structure emerging that is not just like being 0 near convergence. So we consider the following setting. We assume that the average of the norm of a step is going to be small when averaging across batches. Okay, so the expected next step is assumed to be small. So we want to understand what kind of structure can we get from that. So the step looks like that, and we assume that the left-hand side is small. So on the right-hand side, we have VK times some quantity minus some sum of matrices. Okay? And because we assume that the network is one-dimensional, then basically what we get is VK times some scalar minus some sum of weighted sum of the gradients of G with respect to VK. Okay, so we have VK times some scalar minus some sum of gradients, basically. And then we show the following result, claiming that the gradient of the rank of the gradient of G with respect to any one of its weight matrices is at most 1. Okay, so these gradients are just rank 1 matrices. And going back to the gradient, we see that on one side we have V times a scalar. On the other side, we have a sum of rank 1 matrices. So we get a rank B matrix. So we have two terms here. We have something that is proportional to VK. And on the other side, we have something that is rank at most B, which is the batch size. And we assumed that on average, these gradients are small. So in a sense, we get a trade-off here. Okay? So we have VK is kind of proportional to a rank B matrix, assuming that these gradients are small. We also see, we could imagine that if we take B to be smaller, then we expect the rank to be smaller in that case, but at the same time, maybe it's harder to minimize the gradients. And also weight decay has some effect here, because if we increase the weight decay, then we expect the derivatives of the losses to be larger. So the coefficient of VK, the scalar here, is growing with the weight decay, and so on. But essentially, what we see is that we have this trade-off emerging between the batch size, the optimizer, and the weight decay. So as a next step, we wanted to see experimentally if these intuitions actually materialize in practice. So in our experiments, we train models on CIFAR-10 for 500 epochs, and basically we fix all of the hyperparameters except for, let's say, the batch size or any other hyperparameter, and we try to understand how varying this hyperparameter is going to change, to affect the rank of the learned matrices. Okay, so basically we report the average rank across the weight matrices along the network, and the rank is just computed as the number of singular values that exceed a certain threshold after normalizing the weight matrices. Okay, so we look at these VKs. So in these plots, for example, we see that like x-axis is the number of the epoch, and the y-axis is the average rank, and we train the model, the same model with the same hyperparameter while varying the batch size, and we can see that when decreasing the batch size, then the rank decreases accordingly. So for smaller batch sizes, we expect to have smaller ranks. So we did it for 2 cases here, corresponding to 2 different learning grades. Okay, so this is like a very simple 10-layered MLP of width 100 trained on CIFAR-10. And we also considered what happens when varying the weight decay. So we trained ResNet 18, and we vary the weight decay in this case. And we have 2 plots here for batch size 4 and batch size 16. And we can see that when considering larger weight decay parameter, then we get smaller and smaller average rank. Okay? And interestingly, we can see that if we don't incorporate weight decay, it seems that we have little or no rank minimization. So the effect on rank does not seem to occur when we don't use weight decay. So it's kind of necessary in a way. And we also see here that using the smaller batch size gives us, again, the smaller rank. Okay, so some more evidence for that. Yeah, and then we try to understand whether there is a connection somehow with generalization. So essentially, we can kind of see that there is a tendency where if I alter a certain hyperparameter, let's say I take the batch size to be smaller, or I increase the weight decay, then I get smaller rank. But obviously, if I take these constraints to be too strong, then eventually the train would deteriorate. I would get very bad train accuracies. But if I consider cases where I vary a certain hyperparameter, but I can ensure that I have a fair comparison, so all of my models have 100% accuracy on the train, then if I compare their test performance, I can see that the one with the lowest rank is the best performing one at test time. Okay, so that in this case, it's the one that corresponds to having the smallest batch size. Okay, and so basically the dashed lines are the test performance, and the undashed ones, the continuous curves, are the train performance. Okay, but at the same time, we see that even when we don't have this rank minimization constraint, the networks are able to perform quite reasonable. It's not like it's necessary to have this constraint in order to obtain a certain reasonable degree of test performance. So to summarize, basically we see that kind of hyperparameters regularize the rank. Empirically and in a way also theoretically, we see that this the weight decay or regularization, even very little regularization, is necessary to obtain this rank minimization constraint that we see. And we also see that the batch size, weight decay, and the learning rate have some regularizing effect when they're working together with weight decay. And there is this question that comes up whether we're able to use this idea to translate it to a rank minimization or rank regularization technique, which is, in general, I would say, a hard task to do because rank in itself is a discrete quantity of matrices. So it's non-trivial how to do it. And moreover, we show that generalization occurs even, we know that generalization occurs even when we don't use weight decay. So, it seems that rank minimization is kind of related to using weight decay. So we kind of refute, or at least show some evidence against this hypothesis that maybe rank is the explanation why neural networks are able to generalize well in practice in spite of overparameterization. Yeah, and now I'm happy to take questions.
Thank you. Let's do one quick question while we set up the next speaker.
Would your theoretical analysis also suggest that you would have a connection between rank and batch size for linear least squares? Do you use the nonlinearity in your theoretical analysis, or it also applies to?
So in least squares, you have like a one-dimensional function, right? So it's in and of itself already rank 1, right?
Well, no, high-dimensional.
High.
Oh, I guess, well, you can have multi-class.
Yeah. So, so in that case, so in the multi-class case, I think what you get is a factor of the number of classes. So I showed the case where you have like a univariate function. So the lemma that I showed of the gradient of the network with respect to the input is going to scale with the number of classes. So.
I guess the reason I'm asking, like for linear least squares, you wouldn't expect the batch size to affect generalization. So I was wondering if your analysis had something specific to nonlinear case.
Yeah, I'll have to think about it. Yeah. You mean like splitting the... like you split the row and the normalized regular. Yeah, so that's actually a good question. So we started by looking at like the standard regime where you have like training with SGD and weight decay. And in that case, you also can get a bound, but the bound scales with 1 over the weight decay degree. So you get vacuous bounds. So we are trying to explore this new direction that seems more promising. Yeah, it's still open. Yeah.
Thank you so much.
Thank you.
Okay, so now we have the last contributed talk of the day, and after that we have another invited talk. Now we have Ido Ben Shaul, and he's going to talk about neural collapse. So thank you. Can you hear us?
Yes,
Perfect.
I can hear. Can you hear me?
Yeah.
Yes, thank you. Okay, so hi everyone. Thank you for the opportunity to speak here. My name is Ido Ben Shaul, and today I'll be talking about intermediate neural collapse and generalization. So this is joint work with Lian Galanti and Tomer Galanti. So I'll start off by defining neural collapse and just giving a quick intro. So Papian et al. Showed in this paper that if we take a large overparameterized neural network in the classification setting and you train it with SGD and weight decay, several geometrical phenomena happen in the penultimate layer. So we're going to focus on some of them, and mainly that the feature embeddings of samples from the same class cluster around their class means. So in this diagram, if the small balls, if they represent samples from the features and different colors represent different classes, then we're going to see a clustering around their class means. And in this cartoon, we actually see the process between the layers. So they start off random, and we see this clustering around their class means. And at the end, we have something we call variability collapse, where all the points from the same, or all the samples from the same class are mapped to the same point. So why do we care about neural collapse? And can we relate it somehow to generalization? Now, I'd like to point out that we can actually measure the amount of clustering that's happening in the epochs and in the intermediate layers. So we're going to see this soon. So the first question we can ask is, does neural collapse imply generalization? Meaning that if we have some neural network and we check how much it collapses, can we say how well it will generalize to new samples? And in this paper by Tzu et al., they showed that even when we train with completely random labels, we actually get collapse. So here they have CFAR10 with several different networks, and we see that they reach perfect collapse. So one might think that our conclusion is that neural collapse does not imply generalization, and we can go home. So we ask a slightly different question. So maybe neural collapse is indirectly connected with generalization. And our intuition is that neural collapse actually hints at the actual complexity of a trained neural network. So I'm going to formalize this in a bit, but I'd like to give you the intuition. So here we have networks that are trained on CFAR10 with a convolutional neural network and a constant channel size of 400. And each one of these lines is representing the amount of clustering in different intermediate layers. So this is the first layer, the second layer, and so forth. And we take varying depth and train the same network. And what we see is we see that the clustering monotonically increases until we have some saturation. So after something like 7 layers, we're already getting collapse. And we see that the saturation happens the same in each one of these networks. So we get the intuition that this collapse metric actually helps us understand how many layers the network actually needs to fit this data set, and the top layers are redundant. So I'd like to formalize this just a bit. So we have a training set S, and it's composed of these SCs, and these are all samples of class C, and a mapping from the input space to an intermediate layer. So we can define our trained class means mu f of SC, just the mean embedding in this intermediate layer of all samples from class C. And we can define the nearest class center classifier, or NCC classifier, H hat, And it's going to go like this. We're going to take a sample, we're going to run it into this intermediate layer, and we're going to ask what's the closest train class mean. And this is a decision rule, so we can actually look at the test and train error rates and the accuracies. And what neural collapse basically says is that in the penultimate layer, this NCC classifier is going to be identical to the network decision. So now we're able to define our effective depth. So let's say we have a trained neural network of L layers and a classifier at the end. And we're going to define Fi as the network up to layer I. And we're going to define the NCC classifier just like we did before. So the epsilon effective depth is going to be the minimal layer at which this NCC error rate is going to be smaller than epsilon. So we have this clustering going up, and at some point the error is less than epsilon. Now, why does this definition make sense? So this is something we discover in our paper, which we call the minimal depth hypothesis. And what this basically tells us is that there exists some integer L0, such that if we train a neural network of depth greater or equal to it, and we do it again with cross entropy using SVG and weight decay, the effective depth is going to remain constant. So it's going to be L0 no matter how many layers we stack on top of it. So going back to this figure, we have this L0 when it collapses, so something like layer 6. And if we add more layers, we're actually going to collapse in the same place. So we have this minimality through this metric of neural collapse. And how can we use this minimality for generalization? So we use an observation which is quite intuitive and which we see in practice, is that training with random labels, fewer layers reach collapse. So intuitively, if I take a data set and I ask how hard it is to cluster it into two centroids, and then if I take some of the labels and I give them random labels, this is going to be harder to cluster, and therefore we'd expect more layers. And this is exactly what happens. So here I have the same setting. We have a convolutional neural network with 10 layers and 400 channels in every layer. And we look at different noise ratios. So this is noises for the labels. And we see that if we take, let's say, epsilon 0.03, so we see that in the 0% noise, we have collapse after 6 layers. In the 25% noise, we get collapse after 8 layers or 7 layers. And in the 75% noise, we get collapse only in the final layer. So we get the feeling that this metric somehow tells us how much the network is ruined when we corrupt the labels. So how can we use this to actually show generalization bound? So this is something we call the comparative generalization bound. But before this, I'd like to take a minute to talk about traditional generalization bounds. So let's say we have a classifier H. We say that with probability 1 minus delta over some training data S and a sample size M, the error of the distribution is usually bounded of something of this form, which is the error on the train set, plus this form right here, where C of H is the complexity. So it could be the VC dimension, some parameter counting scheme, more recently, the norms of the weight matrices, plus this log 1 over delta term, and divided by the number of samples. Now, usually this is going to be, so we want this to be minimized by the training algorithm, either implicitly or explicitly. And the error on the train should be small because we want to sort of fit the data set. But the problem is that in deep neural networks, this complexity term is quite large. So the number of parameters is huge and usually much bigger than the sample size. And therefore, the bound we get is vacuous in this setting. So let's talk a little bit about our setting. We have some hypothesis class, so some neural network. And we have some complexity measure of this classifier. So you can think of the effective depth here. And we define the minimal complexity for a data set S as the minimal complexity of a classifier that fits this data set. And we're going to need one more thing for our bound, and this is that something we call uniform mistakes. This says that the learning algorithm on a train set for a train and validation set makes mistakes over the validation set uniformly. So both the values of the mistakes and where it makes the mistakes is distributed uniformly. And given this assumption, we can show our bound, and it goes something like this. So we pick some noise level P between 0 and 1/2, and we have some training set and validation set from distribution. They're both of size M. And we assume that the learning algorithm has uniform mistakes on the validation set. And let's say we train a classifier on the training set with gamma initialization. And we define Y validation tilde to be the Y val labels when we corrupt Pn with them. So if P is equal 0.2, we're going to corrupt 1/5 of them. Then we can present our bound. So our bound in expectation of the error on this classifier on the distribution is bounded by these two terms. So let's break it down. This term is going to be the corruption level that we chose. And then we're going to have this probability. So in this probability term, we compare two quantities. So this is why we call it the comparative bound. We compare the expectation of the complexity of this classifier over different initializations with the minimal complexity needed to fit this corrupted data set. So let's look at some examples of this. So if we take, let's say, a large P, so we corrupt our data set a lot. So this term is going to be quite big. However, this data set is going to be very corrupted. So we'd expect that the complexity of our classifier is going to be lower than the complexity needed to fit this noisy data set, and therefore this probability is going to be small. On the other hand, if P is close to 0, so very small, this term is going to be small, but this validation set is going to be very close in distribution to the training set, and therefore the complexity of this classifier is going to be bigger than the minimal complexity needed to fit this data set, and therefore this probability is going to be large. So we get this interplay between the ratio and this comparative term. So this holds for different complexity measures, but the effective depth makes a lot of sense. This is because it's a discrete measure, so we can actually check different values and see when it holds. And this is versus a continuous notion of complexity for, let's say, the minimal weight norms or something like this, where it's hard to estimate the minimal norm needed to fit this data set, for example. And we also have the minimality hypothesis, which in our bound tells us that if we add more layers, the bound doesn't grow. And this is something very convenient for bounds. This is something we'd like to have in general for bounds. Cool. So we have initial experiments with this bound. So we actually estimate it. We do it for MNIST, Fashion MNIST, and CFAR10. And here I show for convolutional neural networks of depth L and 8 channels. So we actually have in the papers more examples. And for each one of these architectures, we have some, this is the actual test error. And we guess different P's, right? So different P's give us different bounds. And we actually get pretty nice bounds. So 0.1 for MNIST, 0.2 for Fashion MNIST, and 0.66 for CFAR10. And this is quite nice since these are very deep neural networks and we actually get non-vacuous bounds, which are relatively tight. So there are two other things I'd like to show about our bound that's I think are pretty cool. So the first, we said that this bound generally shouldn't increase when we add more depth. So this is exactly what we test. For example, for MNIST, we earlier saw with 10 layers, so we look at 12 layers and 15 layers, and we see that this bound is maintained. And this is the same for other architectures. In CFAR10, it actually gets better. So this is something interesting and I guess a bonus. And Another thing I'd like to show is that we actually compare it with some well-known bounds in the literature. And these bounds rely, some of them, on the norms. These are quite big in practice. So the best one is the spectral Frobenius norm, and it's quite vacuous for these networks. And generally, there's a trend of them getting bigger as we add more depth, which is something that our bound is able to circumvent. Okay, so future work includes finding different complexity measures for this bound and seeing how we can approximate them. We'd like to incorporate the width and see how it interplays with this neural collapse setting. And potentially, we'd like to prove the minimal depth hypothesis and see how we can show it theoretically. So I'd like to thank my collaborators, Tomer Galanti and Lian Galanti. And yeah, thank you for listening.
Thank you so much. Do we have any questions from the audience? Yes.
Excuse me, I can't hear the questions. So is it possible to say it with a microphone or something like this?
Yeah, sorry about that.
Thank you.
So there was this assumption on uniform mistakes on the validation data. It seems a little strong to assume. So is that first verified in practice? Like how do you have any understanding on how strong a condition that is to require?
Yeah, that's a great point. So you're right. This is maybe the only assumption here we take, that it's a little bit harder to show. We haven't yet done experiments to show this in practice. We do think that it would make more sense on some data sets versus others. So for example, in things like hierarchical data sets, it might make less sense, right? Because you'd have two classes that are more similar in nature than other ones. But yeah, this is definitely something we'd like to show that happens in practice.
Just a follow-up. So is there any link between an assumption on the data distribution? Are you also assuming that there is some form of uniform measure for all the class marginals?
Yeah, we don't make actually assumptions on the data. So the nice thing about this comparative bound is that we compare how the network behaves on the data set with how it behaves on the corrupted labels of the same data set. So this sort of implicitly includes this info on the data set, if that makes any sense.
Right. So if the data was very skewed to begin with, then to ask a learning algorithm to have uniform mistakes can be near impossible, right? Like if I see 100 examples of class A and only 2 examples of class B, then but in validation data, what is the uniform mistake here mean?
Yeah, so I guess there's 2 parts here. So we do assume that the data set is balanced. So just in terms of the very skewed. But I guess if the data set is very problematic, yeah, then maybe the assumption of the uniformity on the validation set might be less sensible, but I need to think about it. I'm not sure.
Okay, thank you for your time. Yeah, thank you for the talk. Yeah.
Let's thank the speaker again. Thank you. So now we have the next speaker. Let's see if we can have her. She's on Zoom, so we should be able to see her. Okay, that's us. Hello, Sara. Thank you so much for agreeing to give a talk. So we have the last speaker of the day and of the conference. This is Sara Soya, or Sara Soya, as we would say in Argentina. She's the last speaker. She's a professor of neuroscience and physics and astronomy at Northwestern, and her work is in computational neuroscience and statistical physics and statistical inference and she investigates the information processed in the brain. So thank you so much for being here, and we're looking forward to your talk.
Many thanks for the invitation. And I am the only person standing between you and hopefully being outdoors in sunny weather. So we'll just get going. And hopefully I won't keep you very long. So in preparing this talk, I did it in such a way that it would be possible for you to interrupt me as much as you need, and I will not run out of time. So please do interrupt me. This is a bit boring to talk to a screen. I would like to really experience that I'm talking to an audience, and I know that from the last few talks that that I followed, that you can be very interactive and ask many questions. So please do the same here. So let me start. It's going to be a bit of a different talk than the talks that you have heard so far. Because I'm not going to show you a very recent advance with very mathematical tight bounds. What I'm going to try to show you is how statistical physics and statistical inference can come together and provide a very fertile point of view on how to analyze many of the problems that we always discuss when we talk about training multi-layer neural networks. And let me start with this notion of causality, which is a notion that it's implicit in all the work that we do. I think that we look for causality and we look for explanatory models because we have evolved in a world with laws of physics in which causality is the norm. So in the world, there is a dynamics and causality. So events X result in events Y. So there is a link from X to Y, where X could be a function of time and Y could be a function of time. And we think that X causes Y, or X is one of the components, one of the causes that results in Y. Now we are in this world and we have a brain, and our brain is going to be this purple box with parameters W. So as a neural network is. And then when we see an input X in the world, the X would like to result in Y, but X is an input to our brain and causes an action. And as a consequence of our action, the output is actually a Y prime, which is not exactly identical to Y. And the difference between Y prime and Y reflects our intervention in the process. But the most important thing of this point of view, both with human intervention or without, is this idea of X into Y mappings, which we use all the time when we talk about multi-layer networks. We think of input-output maps, and if we think of a function A that maps an input X, it would be n-dimensional, into an input Y, which would be r-dimensional, so that Y is a function of X. And in the particular case of a neural network or any kind of inference system, the function that maps X into Y is actually constrained by parameters W. It's actually specified by parameters W. So again, I use this purple box with parameters W, and I'm going to say that the function that allows me to map X into Y is a function f sub W. And the question that we talk about when we talk about learning is that we don't know these parameters W. We could initialize them, but we could want to learn the proper values of these parameters W. And the information that will allow us to learn comes from a training set. The training set comes in the form of data. Every data point X mu is actually an XY pair. I use a supra-index mu to label the examples. I'm going to talk about having M examples in the training set. And these M examples, each one of them being an input-output pair, is an example of the desired map. So we use this information containing examples to train a neural network. And how do we do that? Well, we say, in actuality, in the real world, X is mapped into Y. But our neural network that has parameters W maps X not onto Y, but into f sub W of X. So what we need is a notion of distance in output space. That's all we need. So that we can say that the error that network W makes on this particular XY example, on this particular pair, is the distance between the output we desired, which is Y, and the output that the network gives us, which is of W of X. One example of this is the quadratic loss that we use all the time, is 1/2 of Y minus F sub W of X squared. But it doesn't have to be this quadratic loss. It could be any notion of distance in output space. In particular, actually, if I'm going to try to be a bit more precise, it doesn't even have to be a distance. It doesn't have to be symmetric. The distance between Y and FW of X doesn't have to be equal to the distance between FW of X and Y. It doesn't have to obey triangular inequality. The only property it does have to obey is that distance is always larger or equal than 0, and it's equal to 0 if and only if Y is equal to FW of X. So this is why we can use all these entropic distances and L1 distances, LP distances. So it's a very kind of weak requirement of this notion of distance in output space that allows us to define a loss function. So given a training set, we have these M examples. Each example is, as I said, an XY pair labeled by this index mu. Mu goes from 1 to M. We construct a cost function. And this cost function is simply the average error over the training set. So in every point in this W space, which is a very high dimensional space where every axis corresponds to one of the parameters that specifies the network, we define a landscape over W space. And this landscape is our error function, the learning error, EL of W, which is the error that network W makes on example mu, sum from mu equals 1 to M, and divided by M, if I'm going to think of it as an average. So most learning algorithms are based on an optimization problem, which is finding special values of these parameters W, which we can call W star, that minimizes learning error. And typically what we do is we look for it by using gradient descent, but we heard some beautiful talks yesterday and today about how we can go beyond that and be a little bit smarter than that in how we find the parameters W star. But at this point, essentially, with just a training set and a notion of distance in output space, we have mapped our learning problem into an optimization problem. So I'm just saying things that you all know. I'm just trying to formalize it a little bit. And this optimization problem is complicated. I mean, you are used to seeing very fancy looking landscapes for multi-layer networks, deep networks. But consider a very simple network in which X maps into Y via a parameter W1, and there is a bias W0, so that Y is just some nonlinear function, some sigmoidal function of a linear combination of X, W1X plus W0. It's a very simple example. The parameter space is two-dimensional. I have the bias W0 on this axis and the weight W1 on this axis. And yet I can construct a training set for this function, which is a learnable function, such that the error function in this very simple two-dimensional space is very, very complicated. So we are all familiar with the intuition that when we look at very high dimensional thousands and millions of parameters in a deep multi-layer network, then this surface in which we're trying to solve the optimization problem is a very complicated surface. But still, what we do is try to use simple ideas to try to solve this problem. So let's stay for a moment in this very simple case where Y is a nonlinear function of a linear combination of an n-dimensional input variable X. So I'm mapping n-dimensional inputs X sub I, where X sub I are the components of an n-dimensional vector X in a single scalar U. So I can add a W0 as a very simple extension from n to n plus 1 if I add an x0, which is always equal to 1, so that I can write Y as G acting on the scalar product between an n plus 1 dimensional vector W and the n plus 1 dimensional X. So even in this very simple case, no hidden layers, I'm just mapping input, n-dimensional input into one output. Even in this very simple case, we can implement interesting functions. And let's assume again that we are in a situation of learning from examples. We have the examples xi mu. Each example is an xy pair, mu labels from 1 to m. What is the error that a given network with parameters w makes on the muth example? Well, that error is 1/2 of y0, y mu, which is the value that I wanted to get, minus g of the value that I really get, which is g acting on the linear combination of wi xi in example mu squared. In this very simple case, of course, we can take the gradient. We can actually, I put a 1/2 here, so I don't have to carry these factors of 2. I get the argument of the quadratic error, the target y minus the y that the network gives me. I get the minus sign. I get the g prime of the linear combination between the w's and the x's. And when I take the gradient with respect to a given wi, a given component of the weight vector, I get xi mu. So we know that this can be written in a very simple way if we just keep xi mu and we define everything else as delta mu. So if we define delta mu this way, then the change that we want to make in the weight, in the ith component of the weight vector, in the weight wi, which is going to be minus a learning step times the gradient, the derivative of the cost function with respect to wi, can be simply written as delta x. So our change in the weight, in the ith component of the weight vector due to example mu is simply the product of the input to the unit, the activity xi mu of the input unit times a delta mu, which is an error associated with the output unit. So it's a synaptic rule which only involves the presynaptic neuron or the presynaptic unit I and the postsynaptic unit, which is the output unit on which we compute this delta. And this rule, of course, was known even before we started doing multi-layer networks for this very simple one-layer structure, and it's called the delta rule. So this is the delta rule that we, of course, extend by using backpropagation, by learning how to compute deltas all through the network, not just at the output level. So this is what we always do. You all know that. So now I want to give you a completely different perspective of learning, which is an ensemble perspective of learning, which is a little bit equivalent to the idea of having a bag of hypotheses. So this is my W space. It's a very high dimensional space. Every axis in the W space corresponds to one of the parameters whose value I need to establish in order to train the network. So let's start with a prior, which I call rho 0 of W, which is properly normalized. The integral of rho 0 of W over W gives me 1. And I could pick any network within this ensemble of networks according to its prior probability rho 0 of W. That's a prior. No examples have been seen so far. So I could think of picking a network within this ensemble as making an hypothesis about what is the XY functionality in the real world. The real world is what produces examples, and is an oracle or a real world that sends me examples. So I have these examples x mu, which are of the form x mu, y mu. That's my training set. And let's say one of those examples, and I'm going to define a masking function over this configuration space. And I'm going to say my masking function on a given point W, given that training example takes the value of 1, if the training example is satisfied by that particular configuration of parameters W. That is to say, if the function fW implemented by that point W in W space applied to x mu gives me the correct y mu. So in that case, the network stays in the ensemble. However, if this condition is not met, that is to say, if f sub w acting on the input x mu does not give me y mu, then I am going to eliminate that with my masking function. You can think of this masking function as an indicator function, which essentially is a survival probability. Only the networks that satisfy the condition imposed by the muth example are going to survive this pruning of networks. So essentially what we do is we started with this W0, with this W space in which there was a rho 0 of W, sorry about that. And then after the first example comes in, rho 0 of W is multiplied by this masking function, theta W of psi 1. So let's say that all these guys are eliminated because they violated the condition imposed by the first example. So I'm left with the rest. But now the second example comes in psi 2, and then this gets multiplied by the masking function theta W psi 2. So after I have seen n examples of the training set, I have to cumulatively iterate this multiplicative process. And what I'm left with is an integral over W of rho 0 of W times the product of theta W psi mu multiplied from mu equals 1 to n. So if I started with the zeta 0 with a volume that I had defined to be equal to 1, because I defined the integral of rho 0 of W dW to be equal to 1, it's clear that this masking process will monotonically shrink my availability of hypotheses, will monotonically shrink the volume of hypothesis, the volume of configuration space that has survived the interaction with m examples. So I have this monotonic contraction of the volume of configuration space as more and more examples are introduced. And I always write larger or equal, so C0 is larger or equal than C1, Cm minus 1 larger or equal than Cm, because it's possible that the nth example eliminates a region that has already been eliminated, and therefore introducing a new example does not cause any additional shrinking of the available volume of configuration space, the available volume of hypotheses that survive having been confronted with the training set. So you could think of this W space as a set of original beliefs, as a set of original hypotheses, a bag of hypotheses about how the world works, how is X functionally related to Y in the world that you're trying to model. And what you're doing here is every time you see an example, you eliminate all the hypotheses that are inconsistent with that example. So that's something that, it would be very useful if all of us did as scientists and as citizens, that when a piece of reality tells us, oh, what you believe was incorrect, if we will be able to discard that belief and stay with the ones that are consistent with the data. But it doesn't always happen that way. Anyway, so what I have shown you so far is a very strict form of learning. It's a type of learning where I require perfect matching. I require perfect answers from the networks in order to keep them in the ensemble, to keep them as part of the configuration space. Of course, we want to be a little bit softer than that. We want to allow for the fact that maybe the data was noisy, and we want to make some allowance for not giving the perfect answer. So let's consider again what was the error that the network W made on example mu. It was the distance between Y mu, which is the desired output, and SW acting of X mu, which is the output produced by that particular network. Of course, if FW of X mu is equal to Y mu, if these two arguments are equal to each other, the distance will be 0 and the error will be 0. And then we say the error of W on X mu is 0, and we want the function theta of W for that particular example X mu to be 1. So that where we were before. But what are we going to do if FW of X mu is not exactly equal to Y mu? We want to then incorporate, in some sense, a measure of the error. We want to incorporate what should be this penalty paid, which is not exactly setting the survival probability equal to 0, not setting the masking function equal to 0, but we want to introduce a survival probability theta of mu of W and X mu, which is going to be an exponential function of this error. So when the error is 0, this is equal to 1. When the error increases, this decreases monotonically as the error increases. So you would think that this is a very ad hoc way of proposing what the masking function should be. And actually it isn't. I'll show you later that there is a condition that allows me to derive this form. There is a condition that allows me to decide that this form is the correct form. But I will show you first that this is a useful form. And by the way, when I show you why it has to be this form, I will also show you that beta has to be positive. So what we have done is replaced hard masking by soft masking. Let's say that this is a cut across W space. So we started with the density given by rho 0 of W. The first example came in and it eliminated all the W's that were inconsistent with that example. The second example came in, it eliminated all the W's that were inconsistent with that example, and I'm only left with a region that is compatible with both Xi1 and Xi2. When I introduce soft masking, I'm not completely eliminating those W's. I am decreasing their contribution to the ensemble. These configurations are attenuated away from rho 0 of W, which was their initial weight, by a factor which is exponentially controlled by the error made on the data. So if Xi1 controls this region, then this is attenuated according to the error that this region makes on example Xi1, and this region is attenuated according to the error that the W's in this region make on example Xi2. So now again, we have a multiplicative effect of a soft masking function. So we go from rho 0 of W to rho 0 of W times e to the minus beta, the error that network W makes on Xi1. And now this gets multiplied by the exponential of e to the minus beta, the error that W makes on Xi2. And I get a factor like that for each example. So now after I have seen the M examples in my training set, I have what survives, what is the volume of the hypothesis that survived, is an integral over W of rho 0 of W e to the minus beta e W Xi mu multiplied by mu equals to M. But of course, we know that the product of exponentials is nothing but a sum of the exponents. So I can write this as Cm equals integral over W of rho 0 of W e to the minus M beta Isabel. And I have a factor of M because remember that I have defined the learning error as an average with the 1 over the M factor. So this is the useful part of having chosen this exponential masking, which is that the product of exponentials gives me the exponential of the sum, and the sum is the learning error. So now what I have is an ensemble of networks that all of them started being possible with probability rho 0 of W, and now they are all attenuated by a factor which is e to the minus M, where M is the number of examples, beta, which is my tolerance to error, and the learning error on W. So this is a way to induce a new density, a new probability density over W space away from rho 0. So when we started, we have an ensemble of all possible networks, all possible models, and it was described by this prior density rho 0 of W. So now, after I have seen M examples in the training set, I have trained an ensemble of trained networks, and this ensemble is described by a probability rho M of W, which is rho 0 of W e to the minus beta EL of W divided by Zm, where Cm is just the integral of over W of rho 0 of W e to the minus beta M EL of W. So the integral of dW rho M of W is again equal to 1. So the partition function that I have here in the denominator is simply providing a normalization constant. And note that I didn't have anything, I didn't have to invoke any kind of algorithm for exploring W space. I have moved away of the problem of how am I going to minimize EL sub W? How am I going to solve that optimization problem? I'm saying giving a landscape Isabel of W defined over W space, this is going to be the correct way of defining the trained ensemble as opposed to defining the prior ensemble, which is the ensemble of randomly connected networks according to the probability distribution rho 0. So this I'm going to show you is very similar to some of the things that Francis Bach was telling you yesterday. But before I do that, let me move a little bit further. So I have used my training data. Every point psi xy was drawn from a probability distribution, which is the joint probability distribution. I call it P tilde. The tilde means real world distribution of xy, which is a P of y given x times a P tilde of y given x times a P tilde of x. The p tilde of x describes the region of interest in input space, and the p tilde of y given x describes the functional dependence that we are really interested in. So now, how do we, this partition function that we have defined, Cm, which is dw rho 0 of w e to the minus beta times m times the learning error, is of course depending on the specific set of data points. So even if we fixed m, it depends on which are the endpoints that we have drawn at random to use as training set. So we assume that these points are all drawn from a probability p tilde of psi. And what we will do is we will take the free energy, which is the logarithm of this partition function divided by beta with a minus sign. And this free energy is going to be averaged over all the possible ways in which we could derive a training set of size m out of sampling the p tilde of psi. So this logarithm of the partition function is a very interesting object, and this is where you'll see the connection with the things that Francis was doing yesterday. This logarithm of the partition function, which because I'm a physicist, I call it free energy, is actually very interesting quantity because you can very easily convince yourselves that a derivative with respect to beta of this logarithm of the partition function, if I take a derivative with respect to beta, it will give me a minus sign and it will give me this sum. But this sum is nothing but the learning error. So now if I knew the free energy, if I knew the logarithm of this partition function, a simple derivative with respect to beta appropriately normalized by m with a corresponding minus sign will give me the learning error. So the learning error is a very important quantity. We always want to know how the learning error varies as we change regularizers, as we change the number of examples in the training set, as we change beta, which is our tolerance of error. But so let's push this a little bit further. So we have a learning error. So again, because I am a physicist, I know that if I have a free energy and a learning error, which is playing the role of the energy, I can compute the entropy. And if I do the algebra for this, it's very, very interesting because the entropy of the process is a Kullback-Leibler distance. The entropy of the learning process is a Kullback-Leibler distance between rho m and rho 0. So is the distance between the posterior rho m of w and the prior rho 0 of w. So the prior is very tolerant, right? We use priors that don't exclude networks because we know nothing and we want to have a very rich ensemble, a very expressive ensemble to begin with. So we expect rho 0 of W to have a large entropy. But of course, we have been excluding possibilities or decreasing the contribution of some of those possibilities to the ensemble according to the error that specific network configurations made on the training set. And therefore, rho m of W is going to have a smaller entropy. So there is an entropy reduction, and that's the way I like to think of learning. I like to think of learning as an entropy reduction process where I start with a very large bag of hypotheses with a very large entropy of possibilities, but little by little, I reduce the entropy of this ensemble. And this Kullback-Leibler distance, because of this minus sign, is actually measuring the amount of information gained, is minus the decrease in entropy. And this distance between the posterior and the prior increases monotonically with the size m of the training set. So this Kullback-Leibler distance will tell me, after I have seen m examples, how much information have I gained from the outside world about the task to be implemented. And therefore, it tells me by how much has the entropy of the ensemble of hypotheses that I started out with, by how much has it decreased. So let's have the following picture in mind. I started with an ensemble W, with which the big purple ensemble was controlled by rho 0 of W, which is the prior distribution. Every example psi is now predictable according to a given ensemble W and introduces a P of W given psi. So every time I see an example psi, I get a probability distribution over W given psi, which is the probability distribution induced in W given psi. So this difference in entropy, which is the entropy of the original P of W, which is rho 0 of W, minus this entropy of P of W given psi, which of course I want to average over all the possible ways in which I could have chosen the example according to, I'm sorry, this should be P tilde of psi. I should have changed that. So this entropy, which is a gain in entropy, right? Because this delta H is positive. This entropy that I start with is larger than the entropy I end with. So this entropy can be shown to be equal to the mutual information between W space, which is the space of the brain or the space of your model, and psi space, which is the space of the world that is sending you examples of the task that you are supposed to learn. And whenever you have a mutual information, you have a duality. Instead of thinking that when I see an example that affects W space, now I can think the complementary manner. If I choose an hypothesis, so I choose a network W, like each one of us is one instance of this possible ensemble of networks W. The choice of W induces a distribution in psi space, which is not necessarily P tilde of psi. It's not a true distribution. It's a P of psi given W. Once I choose an hypothesis or a particular wiring of the network, I'm inducing a probability distribution in the world on the space of examples psi. If I knew the form for this P of psi given W, I could compute the likelihood of the data given my hypothesis. I could introduce a likelihood in space W, which is the probability of the data given W, which is the probability of seeing psi1, psi2, psi_m given W. And if each one of them has been drawn independently from P tilde of psi, that is going to be a product of the P of psi mu given W multiplied from mu equals 1 to m. So any network W in my ensemble is such that I could compute the likelihood of the data given that network. But in order to do that, I would have to know what is P of psi given W. So that's the crucial part that is missing in this. So this is what actually leads me to a derivation of the form e to the minus beta e that I propose for the survival probability. There are two possible approaches to learning. One of them is let's compute the error of the training set. What is the error that network W makes on example mu? Sum from mu equals 1 to m. That's the learning error. I could also think of the likelihood of the data. I would say, what is the probability of the muth example? And multiply that from mu equals 1 to m. I could run an optimization algorithm that minimizes the learning error, or I could run an optimization algorithm that maximizes the likelihood of the data. So now I'm going to make a very strict requirement. I'm going to impose a very strict condition. I'm going to require that when you do that, you automatically do the other. That if your algorithm minimizes the learning error, it at the same time maximizes the likelihood of the data. Or if your algorithm maximizes the likelihood of the data, it minimizes the learning error. So if you require that, it takes about 4 pages of algebra, and I have an appendix on my slides that shows that. If you make that requirement, then suddenly the P of psi given W acquires a form. And that form is the exponential e to the minus beta e of W given psi. This is a probability for a fixed W. This is a probability distribution over psi. If I integrate it over psi, I have to get 1, and therefore I require a normalization constant, the normalization denominator, that for most error functions of interest is going to depend on beta, but not on W when I integrate over psi. So this is why I call it C of beta. And if you're interested, I can post my slides, and then you can follow the algebra in the appendix. Okay, so now I have achieved an expression for this P of psi given W. So now I can compute the likelihood of the data because that was the only thing that was missing was P of psi given W. So the likelihood of the data is now the product of P of psi mu given W multiplied over all the examples mu in the training set. Again, I have the products of exponentials. I get the exponential of the sum. Every time I get one of these denominators, C of beta to the m. So I get e to the C of beta to the m, e to the minus beta m E sub l. So now you see very clearly why minimizing E sub L, minimizing the learning error, is going to be equivalent to maximizing the likelihood. And the two extrema would be in the same place, and for this extrema to be a minimum of the learning error and a maximum of the likelihood, I require beta to be positive. Okay, so now what I have is an expression for the probability of the data given W. So from the probability of the data given W, if I multiply by P of W and divide by the probability of the data, I get the probability of W given the data. But I have the probability of W given the data. That was rho m of W, which was 1 over Cm, rho 0 of W, e to the minus beta em of e beta m, e L of W. So are these two expressions equivalent? Yes, they are. And this is the equivalent between a Gibbs ensemble that is defined by this exponential attenuation with a well-defined free energy, a well-defined energy, which is the learning error, and a well-defined entropy, which is the Kullback-Leibler distance that is measuring the entropy reduction as you learn. And we just have to establish some equivalences. The P of W is my rho 0 of W. That's the probability distribution over the ensemble that I start with. The P of W given the data is rho m of W, is the probability distribution over W space after I have seen m examples in the training set. I can get the likelihood, the probability of the data given W, which is 1 over this coefficient, this mini partition function or scaling factor, C of beta to the m, normalization factor, times e to the minus beta m, the learning error. So from this now, I have P of W given D. I have P of, I can compute the evidence P of D. And then this is essentially what I get is the P of D is of course, the P of D given W times the P of W integrated over W. And the evidence is essentially the partition function, except for this additional normalization constant. So this normalization constant, C of beta or scaling factor, plays a very important role in the next step. We still have to compute one thing because I've told you that the Gibbs probability distribution gives me the Bayesian, prior and posterior. I have told you how to obtain the learning error by taking it, how to compute the partition function, take the log of the partition function, call it a free energy, compute the learning error as a derivative with respect to beta of that free energy. I told you how to compute an entropy, which is the Kullback-Leibler distance between the posterior and the prior. But I haven't yet told you how to compute the generalization error, which is always the big question for a theorist playing in this field. So how do I compute the prediction error, the generalization error? Have we acquired a good model of the brain? Has my neural network acquired a good model of the work? And then this is how we define the generalization ability. Let's consider a new point psi, which was not part of the training data, was not part of this psi1, psi-m training set. And let's compute the likelihood of this test point. What is the probability of psi given the data? Well, psi has induced a probability distribution. I know how to compute the probability of psi given W, and I know what is the probability of W given the data. So given these two factors, if I integrate over W, that will give me the probability of psi given the data. So because I know what the probability of psi given W is 1 over Z of beta e to the minus beta times the error. And I know what is the probability of W given the data. It's just my rho m of W is 1 over the partition functions times rho 0 of W times e to the minus beta, the sum of the errors on the training set. So notice the difference here. I'm summing the error that error W makes on example mu, sum over all examples in the training set. And here I have the error that network W makes on the new example Xi. But when I multiply these two things, as this equation tells me to do, I'm just going to get the sum over m plus 1 points, where the first m are the training set, and the point m plus 1 is the new point, is the test point that I need in order to compute the generalization error. So we can now do this integral. We can write it down. And what we get is, of course, a factor of C of beta that comes out, a factor of Cm that comes out. And I get this integral, dw rho 0 of w e to the minus beta. And I have a sum of errors, as I said, over m plus 1 points, where the new point is the test point, and it appears as it had been added to the training set. So this is, again, a partition function. It's a partition function for m plus 1 points. And I still have the original partition function, which is a training set, is for the training set. This is for the training set plus the test point. And I have this little normalization constant C of beta. So I have been able to compute the probability of Xi given the data. I'm going to use the logarithm of this likelihood, the likelihood of the test point given the data, to define the generalization error. So the generalization error, I take the logarithm of this, so I have two factors, a logarithm of Cm over Cm plus 1 over Cm, and a logarithm of C beta with a minus sign. And I'm going to define this as minus 1 over beta. Minus 1 over beta, this logarithm is a generalization error. Now, if m is very large, the difference between log of Cm plus 1 and log Cm, I can think of them as a continuous variable, so that I can define the log of Cm plus 1 minus the log of Cm as a derivative with respect to m of the log of Cm. So again, I have the log of Cm, which was my free energy, averaged over all the ways in which I could have taken a data set of size m to make it not depend on the details of the training set. I have the factor of 1 over beta, and I have an extra factor, plus 1 over beta. This minus and this minus give me a plus 1 over beta, the logarithm of the scaling factor. So now what I have is what I call a full thermodynamic theory of learning. How does this go? Construct a partition function with this exponential form for the attenuation. A derivative with respect to beta, I take the log, which is the free energy, average it over all the ways in which you have taken the training set. A derivative with respect to beta with a 1 over m gives me the learning error. A derivative with respect to m with a 1 over beta gives me the generalization error. So there is a very nice symmetry between learning error and generalization error in this formulation. But I have this pesky little factor here, 1 over beta log of C beta. It turns out that this pesky factor is very, very, very important. And it actually gives us what our intuition tells us it should be. So let me wrap this up by showing you how this works in a very, very simple case. I'm just going to do a linear transformation from the n-dimensional space into a scalar y, such that y is simply a linear combination of wxi, wixi. So it's w scalar product with x. I start with w is drawn from a rho 0 of w. Every point w is coming from a normal distribution with 0 mean, and the covariance function is diagonal with a sigma, with a variance sigma w squared, and the variance is very, very large. So I want to start with a very generous, with a very expressive probability distribution. Let's assume that the examples are also Gaussian. So the p tilde of x are also drawn from a normal with 0 mean, and a covariance matrix which is also diagonal with a variance sigma x squared. What is, let's assume a noisy environment in which y, for example, mu is a w0, which is the w's I want to learn, dotted into x mu. So this is a scalar product. This is what we call sometimes the teacher network, corrupted by noise eta mu. So now the probability of y given x is again a normal distribution, not centered at 0, but centered at the scalar product with w0 and x for a given example x, and with a variance sigma eta squared, where sigma eta is the variance of the noise. So we want to minimize the learning error, which is the target y minus w dot x, which is what the network gives us, squared, sum from mu equals 1 to m with a 1/2. And when you plug these things in, you get a w minus w0 term, which tells you that you're going to minimize by making w equals to w0, but the error will never be 0 because we'll have this eta squared that will give you a sigma eta squared. You will be, have to deal with the variance of the noise. Well, because I started with a very expressive ensemble, I can take the limit of large sigma w and a limit of large m, and then I can actually compute the partition function analytically, and I can compute the free energy analytically in this example. And I can take the two thermodynamic derivatives that I told you about, and I can again compute them analytically to leading order in 1 over m. They are corrections of order 1 over m squared, but I'm thinking of the large m limit. So what kind of terms do I have? Well, I have terms that scale like 1 over m, which is nice because m is the number of examples and n is the number of the number of weights in the network, is the dimensionality of my W space, because I have n inputs, the input vector x is n-dimensional. So I have these factors of n over m, n over m, n over m. What else do I have? I have beta appearing here and here and here. And I have sigma eta squared, which is the variance of the noise that appears here and here. So what I could do is to change a little bit the notation and think, okay, what is sigma eta squared? I can associate sigma eta squared, the variance of the noise, with an effective value of beta, with an effective temperature. So let me define beta 0 as 1 over 2 sigma eta squared. Let me think of beta 0 as the temperature in the world that makes examples be noisy. So that's the relationship between beta, which is a temperature-like variable in physics, and the variance of the noise. So now I can take my thermodynamic derivatives, and instead of writing sigma eta squared, I write 1 over 2 beta 0. And then I do a little bit of algebra, and I rewrite the thermodynamic derivatives, which now depend on n over m, as before, on beta and on beta 0, instead of having the sigma eta squared. Again, with correction up to order 1 over n squared. And this is the result, even for this very, very simple network. And the interesting thing is that's exactly what we expect it to do. What is the role of beta in this formulation? Beta is a goodness of fitness parameter. If I let beta go to infinity, I'm back to my hard masking scenario. Beta going to infinity, which is 0 temperature, beta is an inverse temperature. Beta going to infinity means I'm back to this masking function where any error is strictly penalized. Any network that makes an error is not allowed to remain in the ensemble. On the other hand, very small beta is being very tolerant to noise. Is saying, okay, e to the minus beta EL, even if your error was very big, beta is very small, so e to the minus, not such a big number, your probability of survival is still good enough. So as we increase beta, as we move to 0 temperature, as we move from soft masking to hard masking, of course the learning error decreases. Right? Because we are fitting the data better and better and better and better. We are more strict about the networks that remain in the ensemble, being networks that actually fit the data precisely as beta goes to infinity. However, the generalization error is not monotonic, and it has a minimum at beta 0. So betas smaller than beta 0 means that we are being very tolerant of error. We're being so tolerant of error that we are being more benevolent than what is actually the error associated with the intrinsic fluctuations of the examples. Beta smaller than beta 0 means the examples are corrupted by noise. This noise has an amplitude, a variance, sigma eta squared, which is 1 over 2 beta 0, but you are estimating beta to be even smaller than beta 0. So you are allowing examples that don't fit the data, allowing networks that don't fit the data way to survive. So in this regime, the generalization error is also decreasing, but it's already larger than the learning error because we are underfitting the data. But in this regime, we are overfitting the data. The learning error gets smaller and smaller and smaller. We're fitting the data better and better and better. However, the generalization error decreases. We are losing generalization ability. Why? Because our beta is too large. We are in an overfitting regime. We are being too strict in penalizing networks because they don't feed the data well, as if the data was to be relied upon with 100% trust and reliability, which it is not, because the data is noisy. So these very simple notions of overfitting and underfitting arise already in a very simple linear network with mapping n inputs into one output, but it would not arise if you hadn't have this factor, this log of pi over beta, which actually comes when you go back to the algebra for taking the derivative of the term that corresponds to, it comes from taking this derivative in the generalization error. So this little term and keeping track of the correct normalizations is crucial for devising a theory that has this competition between this beta, the generalization error increases with beta, but it also decreases because of this log of 1 over beta, and this competition between this linear growth with beta and the minus the log of beta is precisely what gives us this non-monotonic behavior of the generalization error. And moreover, it gives us the minimum at a very meaningful value of beta, which is beta 0, which is 1 over twice the sigma squared of the noise. Let me finish by mentioning another concept in which this plays an important role, which is the concept of model selection and using evidence for model selection. So let me go back to the original partition function Cm and divide by this little c to the m and define a scale partition function, such that the prediction ability, the probability of psi given the data, I can have this, I have an extra one here. So I have m plus 1 of the scaling factors associated with the numerator and m associated with the denominator. So now the generalization error can be simply the derivative with respect to m with the 1 over beta of the log of this partition function. So let's do, instead of a minimization of the generalization error, let's do a maximization of the evidence, using this partition function as the evidence, a properly scaled partition function. So we'll get the factor that we expect to get from the log of Cm, and an extra factor that comes from the log of this little z of b, if we go back to this original formulation. And so now we can ask, when is the evidence maximized? The evidence is maximized when its derivative with respect to beta is equal to 0, which happens to be at the value of beta, which is again 1 over 2 sigma eta squared. So it's again beta 0. So for this very simple case, which is a linear network with an adjustable learning temperature, with an adjustable tolerance to noise, maximizing the evidence is a good hypothesis, or is a good method for model selection. In this case, a selection of the model is a selection of the value of beta, because it coincides with the value of beta that minimizes the learning error. You can use this formalism to convince yourselves in other more complicated cases where you can still compute this free energy and compute the thermodynamic derivatives and obtain the evidence and the learning error and the generalization error. You can convince yourselves that this is not always the case, and that selecting models based on evidence, based on the probability of the data given the model, does not necessarily imply that this is the model with optimal generalization. Okay, so this is a summary of what I tried to tell you today. I tried to tell you, let's start with an ensemble view of all the possible networks, all the possible hypotheses for a fixed architecture, but depending on all the possible ways in which the weights could have been selected. And this is defined by a very versatile rho 0 of W, which we want it to be expressive. So we want rho 0 of W to be broad. We end up with a much narrower posterior rho M of W. We can compute the likelihood of the data, and we can compute the evidence. And this scaling factor C of beta plays an important role in the evaluation of the prediction error, which is what allows us to decide whether the trained network has acquired a good model of the world. And you haven't interrupted me a lot at all, actually, but then we have time for questions. Thank you.
Thank you very much. Very nice talk. Questions from the audience?
Everyone is tired.
Okay.
Hi, thanks for the talk. This idea of decreasing or increasing the temperature kind of reminded me of trading off errors in support vector machines and the like. So I was wondering if the other component of the support vector machine, namely the prior on having a low norm, whether there's sort of a different way of making sense of a limit where you essentially get a support vector machine from this statistical physics treatment.
That's an excellent comment. Thank you. This idea, this beta, this temperature idea, is just really a trade-off. It's the basic idea that you should not keep on insisting on decreasing the learning error. And it's the idea behind early stopping, is the idea behind any kind of regularization in which you add terms to the cost function so that when you minimize the new cost function, which has additional terms which are regularized, you are not going to necessarily find the W star that minimizes the learning error. So it's a very general idea, as you point out, and is this idea of overfitting by insisting on an excessive optimization, excessive minimization of the learning error, which does not take you to architectures or to specified models or to values of the parameters that minimize the generalization error, which is what you really want. So, and the support vector machines are a special case of that, where this is again a single layer network, but we think of it's not a single, it's a 2-layer network with a single layer of hidden units, where we use an expansive kernel in order to define a hidden layer which has higher dimension than the input, and then we do this simple 1-layer regression or 1-layer classification problem on this new expanded dimensionality representation, but the same ideas will hold. If you think that the kernel is fixed, then you don't have to learn the weights of the input to hidden. You only have to learn the weights from hidden to output, and you're back to this very simple problem that I described.
Nice. So, one question. So, what you just mentioned means that there is a formal connection between the bias and the variance of the estimators with this temperature formulation as well, right?
Right. So again, I want you to think of this temperature. It's a very fisted concept, but think of this temperature as how tolerant you're going to be to not fitting the data precisely, because you're doing early stopping or because you're regularizing. So you're not going to be so strict in minimizing the learning error in some sense. You're going to give up. You're going to trade off not doing the optimal minimization of the learning error for the sake of gaining generalization ability. One possibility is to understand that you shouldn't do that because your data is noisy. So it's like, I'm the oracle and I'm producing data for you, but I'm noisy. So the data that I send you is not strictly correct. So it's mislabeled or is corrupted by noise. So if you insist on fitting that data to death, that's not an optimal strategy, right?
So there are some models that have this benign overfitting kind of behavior, where sometimes you can fit the training data perfectly and still have a descent of the risk going to 0 even in overparameterized models. Is that something that can be captured by this model that you mentioned?
So in this very simple model, you would have to go to beta infinity for the learning error to go to 0. But you could imagine other models, because if you work at finite m, if m is finite, or even large but finite, I can always make a model that is expressive enough that will perfectly fit the training set, even if the training set is noisy. But again, there will be a penalty to be paid when you try to compute the generalization error for that model. So the learning error will decrease, go to 0, stay at 0, but the generalization error will decrease and then eventually increase again.
Do we have any other questions from the audience? One more?
Sure.
Thanks.
Thanks for the very interesting talk. If you're not allowed to return an ensemble of functions, but someone forces you to return just a single function, which one would you return?
Well, if you just run a risk minimization, you will return the wiring, the particular set of W's that minimize the risk, correct? That's
Right.
that's what you do traditionally do. But if you include in the risk function that you minimize, in the loss function that you minimize, you include regularizers, you will already be playing with this trade-off between learning and generalization that I described. So I use this ensemble idea to give you a conceptual framework for thinking about these things. Should you use this as an algorithm? That's essentially the question that you're asking me. And you could run a Monte Carlo search over this. You should not do, it's very hard to use a Monte Carlo algorithm to compute the partition function, but physicists are very good at computing free energies, which is the log of the partition function, by doing a Monte Carlo sampling of F space. So if you want to do a truly Bayesian calculation in which you keep the ensemble, you keep the prior ensemble and you keep the posterior ensemble, not just one good representative of the posterior ensemble, but keep the posterior, you will do it by using a Monte Carlo algorithm for sampling the ensemble. But again, not trying to compute the partition function, but trying to compute the log of the partition function, which is the free energy.
Thank you.
Thank you so much, Sarah. Yes, very nice talk. Thank you so much.
Thanks a lot to everybody, and thanks a lot for sticking out for the very last talk on the conference. And I had a great chance to hear most of your talks yesterday and today, and it was really fantastic.
Yeah,
so I hope that you all enjoyed the talks and learned as much as I did. Thank you very much.
Thanks. So, okay, so I'm gonna just give a few closing remarks now, and we can go and enjoy San Diego. Thank you so much for coming. This has been great. I'm very happy, and we had a very nice event with a few hiccups, as you saw. Let's have a special thanks to our organizers and all the speakers and poster presenters and participants that made this conference possible. This is something for you, and thank you so much for being part of this. This is a very nice conference that we just had, and I'm very happy that we could have it in person. And in particular, I want to thank the local organizers who did a lot of work, and it was incredibly challenging yesterday to deal with everything that happened. Actually, you can see the protesters here in this picture, right there. Anyway, and a special thanks to Rajesh Gupta and the San Diego Data Science Institute that gave us the financial support to move the conference here, and everyone else who worked for this event that made it happen, the reviewers for the talks and for the posters. All of you, thank you for being part of this community. And finally, I just wanted to invite you to DeepMath 2023 that is going to happen in Baltimore at Johns Hopkins. So please come, and we'll have something nice to offer to you as well. And that's it. Thanks.